What's up, guys? Today we'll code something really exciting. We're gonna be creating a tool called Toralizer. It's a command line client for connecting to the Tor privacy network. When you run a CLI command for doing a network call, for example curl, the following thing happens. The connect function is invoked and the program establishes a TCP connection to the remote server, and then the communication begins. But with this tool, you'll be able to put the word Toralize in front of any command which does a network call. Toralize will intercept any calls to the connect function and execute our function instead. The traffic will be redirected to a local proxy server, which is a part of the Tor software. It will connect to the Tor network and then to the destination server, effectively masking your identity and helping you to stay private on the internet. And the best thing is, coding this is easier than you might think. Let's get on with it. Okay guys, welcome to this episode. The first thing we need to do today is we're gonna create our own proxy server client. So this proxies, it uses a protocol named SOCKS, S-O-C-K-S. And there are two different protocol versions, version 4 and version 5. And the Tor network and the software supports both these versions. Version 5 is a little bit more complicated, but version 4 should be very easy to implement. And it will be perfect to do it in C. So that's the task of today, creating our own client for that SOCKS proxy and use it to connect to the Tor network. So how do we start? I'm gonna start by logging into my CodePlanet server like this and prepare my screen as I usually do. Today I'm not gonna be coding in Nano or VI like I usually do. This is a little bigger project, a little bit more ambitious. Could do it in VI, even though it's a big project, but I'm gonna be using VS Code today actually. I'm gonna do my while true command so I don't accidentally close down my screen window like this. And since I am using a remote server, I need to somehow either upload my C files and stuff to that server or code remotely in VS Code somehow. And I'm gonna be using a tool which is called the Sociopath SCP client. Like this. If you want to download Sociopath SCP client. It's a tool that uses the SCP protocol, which is basically installed on every server, to upload and download files and subdirectories. And there's also a remote file editing feature that we're going to use today. Okay, so let's begin there. I have started up the program, which looks like this. So I connect to my CodePlanet server and I go to my code folder. So on the left side is my local hard disk drive, and on the right is the files and directories on the server. So I'm gonna right click and create a new directory, which I'm gonna call Toralize, this. And now I'm gonna select the Toralize, I'm gonna right click and I'm gonna click open in editor. Then it's gonna download everything in that folder, which is currently empty, but if it were any code files in that folder, it would download it to temporary directory and open it in VS Code. And each time you save or create a file or a directory inside of VS Code, it automatically updates on the server. Okay, so now I have this emptied here. So I right click and create a new file, which I will be calling Toralize.c. And I will also create a Toralize.h, like this. And I will begin by putting a small header. So Toralize.c, and I will include stdio, create a main, and this time I will type out the longer signature for this main function. That is the argument counter and the actual argument pointer, like this, because I'm not going to be using that in the final version, but the client that we're going to code today, that will be it will be used like this. So if we run it by doing ./Toralize, we're gonna enter an IP address like 1234 and a port. So this tool will connect to a predefined proxy server. We're gonna put that in our H file. Let's do it right away. Toralize.h, and let's put the include in here instead. And in this file we're gonna include our local file. So when the file is in your directory, you use quotes around it, like this. And I save this file. Now, if we go into the sociopath window, we can see in this status bar down here at the bottom, Toralize.c has changed, successfully updated to server. And if we go into our terminal and go into the directory and check the contents of this file, we see that it has updated. The .h is not here yet because I haven't saved it. It uploads on save. So let's do that. And with regard to the proxy server, I will be using the default values for the Tor package, and that will be using the IP address of 127.0.0.1. That's the IP address of localhost. And let's call this proxy. And I will also make a constant definition for the proxy port, which is 9050 as a default setting. Save. And just to verify, now we should have both of these files here. Right. So both the C file and the H file. Great. So let's just create the most basic things first. I will create a char pointer for the host name. That is the host name that we want to connect to at the end, so to speak, the server that we want to connect to. And we also need to have the port number. Let's just do an int for that. Yes. Okay, so first I will just check that argc, if that is less than 3, which means that we don't have 2 arguments specified on the command line. Then I want to print to a file descriptor which is called standard error, which is used for error messages. It's like printing to the screen, basically. And then we want to do like this, usage host port, like that. And as an argument, we're gonna give argv0. So argv0, if we on the command line specify /toralize 1234 port 80, then this is argv0, this is argv1, and this is argv2. And this is an error, so we'll return -1. And if we have our arguments, we will point the host towards argv1, and we're gonna set the port to, and we can't just do it like this, because the port is an int and this is a string. So we need to use a function which converts a number in a string format to a regular number, a to I. Let me just check if that requires an include file, and we do that by doing man 3 a to I. And we need stdlib.h, which I will put in our header file. Include stdlib.h, and I will also put in string.h and uni.std.h. These are the 4 that I always put in every C program that I do. Let's line up this a little bit better, like this. Okay, So how will this work? We need to figure out how the proxy protocol SOX version 4, how does it work? So let's go to Google. And if we want to have the technical specification of a network protocol, we do like this. We search for the protocol name, SOX4 in this case, and we add RFC. That stands for request for comment and is the standard way of describing an official protocol. So that way you will always get the right one. And I'll take the first one here and increase the font size a little bit. This is not a huge file. Some of these RFCs are very big, but it is quite a simple protocol. So there's a two-step process. First, you make a TCP connection towards the proxy server, like any other server, like exactly as you did in my web server video and in the TCP client video. Then when we are connected, we need to create a network packet which looks like this. So from left to right, there is a 1 byte field that is 8 bits for the VN number. And as we can read here, that's a SOX protocol version number, and it should be 4. Then we have something called CD, and CD is the SOX command. It's the code for the command, and should be 1 for connect. So there are two different types of operations that you can do through SOX4. It's a connect operation and a bind operation. So basically a connect operation is when you connect outwards, and a bind is when you prepare for an inbound connection towards you. We are going to do a connect, so we will put a 1 in that field. Then we put the destination port number, and we need to format that port number in network byte order, which is basically that we switch, we cut up the 16 bytes in 2 parts, and we swap them. And same with this destination IP, but this is a 4 byte field, so 32 bits, regular int size, and that's where we put the IP address of the remote server that we want to connect to. And then we need to put a user ID, and I will just put Toralizer there, doesn't matter. And then we need to end that string with 0 byte as usual. And that's basically it. We send that packet, we get a reply, which looks like this, and the only interesting field is this CD field. If that is 90, then the connection has been established, and then you can just send whatever you want. If we get another number than 90, then something went wrong, and we need to deal with that. And then we will send some data just to see that it works. So that is what we need to do. Okay, so I will do like this. I will copy this, and inside our header file I will create a comment block and paste in this one. I want the last line as well, so I see the number of bytes. I think I need to change the size here. Okay, this way we see enough. But in order to be able to create a structure that corresponds to this design, we need to be able to create fields that has the 8-bit size, the 16-bit size, and the 32-bit size. So let's start there. We will use the typedef command to create our own variable types, which will be called int8, int16, and so on. So if we begin with the int8, that's basically an unsigned char in C. That's 8-bit size. So we'll type typedef unsigned char and then our name for it, int8. Then we need the 16-bit size, and that is an unsigned short int. We'll call it int16. And then we need a regular 32-bit int. So that's an unsigned int. And we'll call it int32. Okay, so now we have the different parts that we need. Now we're going to create the actual structure for this packet. So we'll create a struct, which I will call proxy request. And the first is vn, so int8 vn. And the next is cd, which is also an 8-bit. Then we have the destination port, which is 16. Is port. And then we have a 32-bit destination IP field. And then we have the user ID, which has a variable size, but I'm gonna create a username of 7 characters, because that way we can have a 64-bit variable here, which ends in a 0 byte. So that's why 7 and not 8. So basically I will do unsigned jar user ID 8. And this is all we need for the first structure. Let's create the other one at the same time. This one is a little bit smaller, so struct proxy response, and we're not going to be using all these fields. So if we look at this one, the VN is always 0. And the CD will have the code. So the CD is the only interesting field here, because the remaining fields are ignored. So destination port and destination IP are ignored. But we still need to have them defined because we need to have the right size of this packet. So I will do it like this. I will start by creating an 8-bit integer for the VN and an 8-bit CD. Then I will just do int 16 and an underscore character, and then int 32 and 2 underscore characters. We could name these according to this, but I think this clearly shows that they are not important. Okay, so now we have our two structures. We can remove those comments. And make this a little bit bigger again. And I want to create a type def for these structures, so we don't have to type the whole proxy request every time. And I will just call this rec with a big R. And same here, type def struct proxy response, and this will be res with a big R. Okay, so now we have prepared everything we need basically in this file. And we do need a couple of includes though, because we are going to use the following functions. We will have a socket to initialize the socket. We're gonna have connect, and we also need close, hton_s, and inet address. So remember what I told you about the network byte order. So if we have a port number, for example, like something like this in binary, so this is a 32-bit, no, sorry, 48. This is a byte. So if we do like this, let's say this is a port number, and I don't know exactly what it corresponds to, but let's say for instance that it's 9050, because it's a 16-bit field, so it looks something like this. Then we need to copy this right part and put it to the left. That is network byte order, that we have the most important bits first. And that is what these two functions are for. hton_s does it for the port number, and the inet address takes a string and creates a big. So basically it first takes this IP address and translates it to a big number, and then it makes this network byte order. So these are the functions we need. Perhaps I have forgotten any other ones, but that will be clear when we get to that point. So let's find out what include files we need. Let's begin by socket. We do man to socket and y2 because this is a system call. That's what. How do you know if it's a system call or a library call? Try a library call first, a 3. If you don't get a hit, or if you get a hit that doesn't seem right, try the 2. Okay, so we need syssocket.h. I'll just copy it right on. This, and then we need the connect. That's also a system call. So man to connect, and that's the same. We don't need it again. And what else did we need? Close. I think that's unistd that we already have, but let's see. So the close, that is also a system call, and we use it to close down the connection. Can also be used to close down a file. Yeah, unistd, we had that already. And then we need the hton-s and inet address. So man, this is a 3, so hton-s. This one. And finally, inet address. Also a library call. So 3. Here we need a couple of include syssocket we do have already. ARPA inet we do also have, but not net inet. Okay, so let's see if this compiles. Since we are using a couple of files, I think I'm gonna create a make file as well. So I will create a new file and I will name it makefile with a big M. And then I will just put in all gcc toralize.c -o toralize. We're gonna be adding a lot of stuff here later on, but for now this ought to do it. So let's save. And when we have a make file like this, then we don't need to issue the gcc command every time. We can just do make, and then it will try to compile. Okay, typo. So let's go into the toralize.c, and this should be an if, not an int. Let's save, and we'll run make again. This time it compiled our tool. Okay, so the next step is connecting to the proxy server, because we're not gonna create a TCP connection directly to this host and port that we specify on the command line, we are going to connect towards the proxy IP address from the H file and the proxy port 9050. So that we have done before, creating a TCP client. It's exactly the same as before, so I'm gonna make it quite fast. If you need to learn how to do that, you can watch either my TCP client episode or my creating your own web server series. I will explain by haste though. Okay, so we need a couple of variables. First of all, we need an int, which is called s, for the socket file descriptor return value. We also need a structure, which is called sock address in, and I'll call this sock. That's where we specify all the IP addresses and stuff. Okay, so let's start by creating our socket. So s equals socket, and this is pretty standardized. We always put in sock inet, and second argument is sock stream for a TCP connection, and then a 0 for the third argument. And if this s is less than 0, then I will use the p-error command to easily print an error, and we will specify which function that produced that error. And then I will just return -1. When we create the final version of this, I'm going to use more accurate error codes, but for now we'll just do -1 for everything. Then we will prepare our structure, and that's 3 things we need to add in order to make a TCP connection. First of all, we need to put the SYN family to AF inet. We need to put in the SYN port and use the HTON S, so we get it in network byte order. And then we will just put in our port variable here. And finally we will put in our sock SYN address S address, and that will be equal to inet address and our, no, not our port, it should be our proxy port, and it should be our proxy IP address, nothing else. Okay, so these are the 3 things. Now we need to initialize the actual connection with the connect command. So we do connect, and we reference the socket. The second argument is our structure, and we need to create an explicit typecasting, because we need to change it to sock address struct, a pointer to a sock address struct, and we also need to send the reference. So let's put an ampersand there and the sock, and then we need a size, and I will just do size of sock. That ought to do it. Okay, so this line will connect to the server, but I will also need to do an if statement so we see if it succeeded. And this should return a 0 if it works. If we wouldn't remember that, we can go into the command line and do man to connect and go towards the bottom, and here we will find a section for the return values. If the connection or binding succeeds, 0 is returned, otherwise -1. So I will just do a simple if statement. There's no need to save this to a variable. So if this is not 0, something went wrong. And then we do p error. Connect. And return -1. Otherwise, we are connected to the proxy server. So I will just echo that to the screen so we know what's happening. Then I will close the connection because I want to see if it works. So close S. Return 0. Okay, let's see if we did something wrong. Make it compile on the first run. That's not every time. And let's run it and see what happens. Right, we need to put something here. We're not going to be using that information at the moment. Connected to proxy. Great, so it works. So now we have successfully created our TCP connection towards the proxy server, and the next step is to create the proxy request packet according to this structure that we created before. We haven't created any function declarations, so let's do that as well. So we have a main function, takes in an int and an argv pointer, and when I create those signatures, shard, of course. So if we look at our regular main function, we use this format right here. So a char array of pointers. But when I create the type signature, I usually use this format. Doesn't really matter. Okay, so that's the only function that we have this far. Our other function is going to return a pointer to a request. And let's name this function request. And as arguments, we're going to take in a char pointer, which is our destination IP, and just a regular int for the destination port. And let's make both of these const as well. The const keyword means that we cannot change these variables inside of the function. So it's just input values. So this is the signature. I'll copy this and then I will strip it down so it looks like our main one, because we don't need to have the names of the variables when we do a function declaration. And why do we do these function declarations? Do we have to? No, we don't have to. But imagine that we put our main function in our C file at the top. If we then try to reference the request function, it's not going to find it because it hasn't been defined yet. But if we put our request function on top of the function declarations, then it will work. So that's one reason. But I think a more important reason is so you can have like a better look. You can just watch the .h file and you see the entire structure in a very good way. So always do this if you have multiple files or a big .c file. Okay, that was a small parenthesis. Sorry, I copied over this one. There we go. And then we go into here and we will create this request. So what do we need in order to do that? Well, we need to allocate the memory for this request structure that we're gonna return, and we are gonna reference the length of the structure a lot of times. So I'm gonna create an alias for that, or a macro, and you do that using the define, and then you give it a name. I will call this rec size. And what is rec size? It is the size of struct proxy request. And let's create one for the other one as well then. Define a res size, response size, and that is size of struct proxy response. In that way we don't have to manually type out this as soon as we need to reference the size of the structure. And now semicolon at the end. Oh, I misspelled. There we go. Okay, so back to the .c file again. And I'm gonna create a request pointer. I'll just call it rec. Sorry. And I'm gonna start by allocating the memory for this structure. So request equals malloc rec size, like this. And now we're gonna fill this structure with the correct data. So let's bring up the RFC again. So the first thing is the VN, and the VN should be 4. So rec VN equals 4. And if you're not familiar with this arrow, that's basically the same as the dot format. But when you're using a pointer to a structure, you use this arrow to indicate that we need to grab into the reference in order to get the value, or set the value in this case. Okay, so VN is 4. Then we have the CD, and it should be 1 because we're making a connect request. So rec CD equals 1. Then we have the destination port, and we need to put it in the correct format. So rec dest port equals, and now we use this hTone-s function that I talked about before to switch it to network byte order, and it is the destination port. Then we take the destination IP, so rec destination IP equals inet address destination IP. And then we need to have a null terminated string with our variable, and I want it to be 8 characters. So let's create a definition for that. Find username Toralizer, because we need to remove this E. So 1, 2, 3, 4, 5, 6, 7, and then a 0 byte at the end. So I will use string copy to copy into the rec username the username, and the maximum size is 7, and then it will add the 0 byte. Let's do 8. Okay, so now we have prepared this structure. And now we will simply return it like so. And now it will be very easy to handle this, because we have a function which just creates the entire data that we want to send, and we know the size of this structure, so we can just use the right system call in order to send it. Okay, so now that we have our function which creates the packet that initializes the proxy connection, now we're going to use it. So let's go into our main function and let's create a pointer of our structure request type, so we can use it when we want to send the data. And instead of just closing the connection like we have done here, we're gonna set our request variable and use our function. And our request function takes two arguments. It is the destination IP and destination port. And we do already have variables for that. It's the host and port variables. So we'll just use them. So host and port, like this. So now the rec variable is pointing to our packet, and we just need to send it using the right system call. The first argument is our socket file descriptor, which we named S. The second argument is the buffer, and I think we only need to do rec. Perhaps we need to do, yeah, we probably need to do a type definition, typecast I mean, but let's put it like this to begin with and watch the warnings and errors when we compile it. That's usually the best workflow. And we need the size of the packet. And since we know that we always want to use a 8-byte an 8-byte buffer for the username, we have a constant size of our request packet. So we will just use that definition that we put in here somewhere. It is, I think we created a macro. Yes, rec size, that's the one. That is the size in bytes for how big this packet is. So now we send that packet, and the next step in the process, if we look at our RFC, it is accepting this structure back. So we can look inside of the CD property and look for the 90 code. So how do we receive this one? Well, we did use write in order to send the data, and we will use read to receive the data. And for that we need a buffer. So I think the easiest way will be to just create a variable on the stack for that. So buff, and then we'll put the response size as the number of bytes. And before I use read, I always want to make sure that the buffer is empty. So I will memset the buffer with zeros and use the res size, number of zeros. So now we have a clean buffer that we can read data into. Yes, so let's do read, and the first argument is the socket file descriptor, second argument is the buffer, and the third is the size, like this. And if this read operation returns something less than 1, because the number of bytes should be returned, then we know the operation has failed, and we need to show an error. Sorry, I'm a little bit used to the JavaScript strings. There we go. And let's free the buffer. No, not the buffer. Free the request packet, so we don't have things lying around on the heap. And let's close down the socket file descriptor and return -1 for now. So this is if the read operation fails. If it has succeeded, we should have a packet that looks like this in our buffer, but we can't easily access the values inside of it if we only have a string pointer. So we need to create another pointer of the correct type, which is our structure for the proxy response. So we will create a res as well as the rec. And we should just be able to point this towards the buffer. And that's what we'll do. So res equals buffer. I think this should be enough. And now we should be able to grab this value, the CD value. And I like doing it like this. I will create an int, which I will call success. And this will be a Boolean variable. But as you know, we use ints as Booleans. We can use char and other types as well, but usually it's int. And this will be used as a predicate. I'm not sure if you are familiar with the term, but a predicate is basically a function or an operation that returns true or false. And this is American English. I think in the British world they use the word property for this. But since we already use the property term when we describe other things, I think the predicate is a better term. Anyhow, then we can do something like this. So we set success equal, and we go into this structure and we check for this CD value. Now we'll put this in parentheses, and we do like this. So what does this mean? This means that if the CD is equal to 90, then success will be equal to true. If it's not 90, success will be false. Which means we can do like this to to see if it has worked or not. And then I want to print out an error message of my own. So I use the fprintf to the standard error way. And I want to say something like unable to traverse the proxy error code, and then the error code. I need to divide this a little bit. I'm not sure you know it, but if you have a large string, you can always divide it by smaller strings and put them on different lines. Make sure to encapsulate them in quotes on both instances. And then we will show the res2cd value like this. And we can also do, let's close the S and let's free the rec and return -1. And unless this if clause happens, we have successfully traversed the proxy. So let's inform that with a printf, at least for now. Perhaps we will remove these messages when we are done. Okay, so successfully connected through the proxy to and we will have a %s colon %d, and then I will use host and port like this. And now I will close down the connection. When we finish this program off, we will not be closing down the connection. But since we are only checking right now if it works, if we are able to connect through the proxy, we can close down everything and terminate when we are done. So this code will be removed in the final version. And we will free the rec and return 0 like this. The indentation seems to be a little bit off. Well, we'll see if we get an error. Okay, so let's compile this and see what happens. Okay. And when we are troubleshooting code, especially when we have coded quite a lot of lines of code since we last compiled, always look at the first error, because sometimes if you fix the first error, all the other errors goes away. So don't get discouraged when you see a full screen of error messages like this. Just focus on the one at the top. So what does it say? Rec has no member named username. Interesting. So let's go into our H file and see what we've got. User ID. Okay. Yes, of course. So where was that? That's probably inside our request function, right? Yes, here it is. So user ID. Like this, okay. And before I run make again, I press enter a couple of times. So we get a barrier. That way it is much easier to see where the last couple of error messages stops and the new batch starts. Okay, so assignment to res star from incompatible pointer type. Res equals buff. Okay, that's the one I was a little bit unsure about, remember? And I said, let's compile this and see what it says. Because in some of these cases, the C compiler will perform an implicit typecast in this case and work it out anyway. But not this time. So okay, so res is a struct pointer and buff is a string pointer. So what if we were to just do res like this? Let's try that first. Seems like it worked. Okay. So close S, data definition has no type or storage class. That's an interesting error message. Data definition has no type or storage class. Close S. Int close, int fd, uni std. Do we have all our include files? I have never seen that error message before. Uni std, yes. Didn't I call that variable s? Yes, and that's an int. Int. It was only a warning, but a very weird warning. Perhaps something else is wrong in its proximity. If success, fprintf, and the parentheses, then we have the string, and then the end parentheses, close s. What line did it complain about? 94. Okay, it's not this one. It's complaining about this one. Well, there is. Okay. So, let's see. If success, and then we have this, close S, close rec. Yeah, this shouldn't be here. Okay. Let's do this again. Okay, it's compiled. Let's see if it works. So what shall we connect to? I will just do one of my web browsers, and you might have noticed that we didn't put any DNS related stuff in this one. So I can't just put in www.networktechnology.org or something like that. That's something that you probably can add by yourself. See that as an extra task. But for a proof of concept, it's not really necessary. Okay, so I will take the IP address of my web server and let's run Toralize against that on port 80. And if this works, we should see a message that we have successfully connected to the proxy, and we should also see a message that we have successfully connected to the end host through the proxy. Connected to proxy, successfully connected through the proxy to blah 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 blah. Okay, very nice. So this has accessed the web server through the Tor network. And let's add some functionality so it can send some data and read some data, so we can see that it can communicate with the end host as well. That is also stuff that will be removed in the end result. So let's create another buffer. Let's call this temp, and let's do 512. Since it's only temporary, I will not think much of it. So here we are successfully connected, and now I want to send something. So since I'm connecting to a web server, I can use the head command just to grab the information about the web server versions and stuff like that. That's quite easy to do. So I'm going to use the smprintf in order to create the buffer. But first I want to use the memset in order to zero the entire buffer. So, no, not buffer. I need to remember I call it temp. And 0, and the number is 512. And then I will do snprintf, and we are gonna put the result into the string variable, the buffer, that we call temp. And we won't be writing more than 511 characters. And what do we want to put there? So let's do head HTTP like this, and we'll end by RN. And on the next line I will put in host network technology.org. And if you wonder what this RN is, sorry, that is the Windows standard for new lines. So this R thing is a carriage return, which jumps down and goes to the left, or it goes all the way to the left. And the N is, as usual, the line feed. Okay, so now the buffer contains this data. And then we will just simply send it. So write s temp, and I'll do the string length of temp like this. And then I want to zero out the buffer again, or not the buffer, the temp. And then we want to read the results. So we read from S into temp, and no more than 511 bytes. And then we'll just print that to the screen with a regular print S like this. Let's put it in single quotes as well, so we see if there's something weird going on. That's a good tip, by the way. Like if there's a line feed before the data or something like that, then we will see it like this. So this will be on one line and this will be on the next line. Okay, save, and now we will compile, and let's run it again. And this is the response from the web server. As you can see, it works. We are able to communicate through the Tor network, and if I connect to my web server, we should be able to check the logs and see what IP address the requests came from. Var log Apache. Here we are. And let's do tail-3 access.log. Okay, so here is our head, and if we grab this IP address, we see that it's some kind of German address. And we can also do, if we restart the Tor server, so we do etc init Tor restart as root, restart like this, then we issue the same command again. We did get the output like before, and if I check the logs once again, we get another IP address this time. And if we do a host on that IP address, we see that this time it's in the Netherlands. So our program works fine this far, but at the moment, it's just a proxy server client. It's not doing what we intended it to do from the beginning. You remember, I want to be able to do something like Toralize and then run any command like curl against some IP address, and then I want to intercept the connection. I want to run this command as is, but I want to intercept the connection that the actual program does and run my code instead. So it tunnels through the Tor network any program that we want to run. So we can do Toralize and put anything here. We could do like, if we have Firefox installed in the same directory, we could start Firefox with Toralize, and then it will be tunneling through the Tor network. And we could do Telnet or SSH. That is what I want to do. And that is the next step in this process. It seems really advanced, but you will see that it's quite a bit easier than one might think. So what have we learned today? Today you have learned how to create a SOX version 4 client and use it in order to connect to the Tor network. And next time you're gonna learn how to create this nifty little tool that I call Toralize. If you like this episode and want to see the continuation or other stuff in this channel, please subscribe to this channel and hit the like button if you think I deserve it. And thanks for watching, and thanks for today. Welcome back everyone to today's class. Today we're going to talk a little bit about something called XOR. So XOR is an operation. You can do plus and you can do minus and then you can do XOR. But XOR uses two streams of bits and it produces different output bits depending on the input. So if we have two zeros, then the result is 0. If we have a 0 and a 1, then the result is 1, no matter which is which. But if both are 1, then it is 0. So why is this useful? Well, this means that if we use this technique in order to encrypt something, then we can decrypt it if we supply the ciphertext with the same key as when it was encrypted. This is a very basic form of encryption that is only for demonstrational purposes. It's quite easy to crack with today's technologies and computer power. However, it's a good example on how to use XOR. And in this example, I will only make it so that you encrypt one single character. And when you know how to encrypt one single character, there shouldn't be a problem for you to modify the code so it can be able to encrypt any length, but only one character in this example. Alright, so let's begin by
create an xor.c file. And we will also have a couple of definitions. We will define the key, which also will be one character, and we will define what we want to encrypt. So let's define the key as the character X. Let's do big X. And then we will define the clear text as the letter A. So we want to encrypt the letter A using the key X. And we don't need a whole lot of includes. I will just put the standard input-output age library. And in order for us to be able to see what is happening, I will create my own function called print char, which will print the character and the hexadecimal value. And it will also print a text string describing what we are printing. And this will just be a single printf line, something like this. So we will take the character and show its ASCII character code. And we could do hexadecimal, but I think, yeah, let's do hexadecimal. And it will take 3 arguments, the text describing what we are doing, and then the character twice. So we'll print the actual character and its hexadecimal representation. And I will put a 0x in front of it to show that it's hexadecimal. And that's all. Okay, then we go to our main function where we will do the magic, so to speak. We will create a couple of chars, one for the clear text, one for the key, one for the cipher text. Hard to write that word. And one for the new clear text, because we will decrypt it into a new variable. Okay, first we define the clear text as our clear text definition. This one. And we will use our print char to print the clear text before we do anything with it. Then we will define the key as our constant key and do the same. We will print that on the screen. And then we will do the actual encryption. So the cipher text should be equal to clear text XOR key. So this little caret character here, is not what you might think it is. Sometimes we use this caret character to do when we do like x to the power of 5 or something like that. But in C, the caret character is equal to the XOR operation. Okay, so now we have created a ciphertext variable containing the encrypted text using the key. Now we want to print the result, ciphertext and ciphertext. And finally, we'll try to decrypt the text into another variable. And this time we'll take the ciphertext and XOR the key. So as you can see, the exact way that it goes forward when we take the clear text, XOR the key, producing the ciphertext, we now take the ciphertext, XOR the key, to produce the clear text. And then we will use our print char function to print our new clear text. And that should just about be it. So let's compile this one. Oh, I did something wrong. main. That's not right. There we go. Okay, now what? Line 47. I added a parenthesis too much. So let's jump to 47. Okay, it's outside of the text, but I did see it on the message. Where is it? Right here. That should be there. All right, now it works. So let's run it. Okay, so from the beginning we have the letter A as a clear text, and that is 41 in hex. And we have the key X, which is 58. When we combine them together with an XOR operation, we get a ciphertext with a hex representation of 19 and no ASCII representation. And then we XOR the text backwards using the ciphertext and the key. And then we get a new clear text with the letter A, 41. So our code works just fine. Should be cat, not car. Okay, so we do two definitions. We create a simple function in order to print out the results. We set the clear text and print it. We set the key, we print the key. Then we do the encryption algorithm, so to speak, using clear text XOR the key and printing that out. Then we do it backwards. We do the ciphertext, XOR the key, and get the new clear text and print that out. So today you have learned all there is to the XOR operation in C. Thanks for watching, and thanks for today.
What's up, guys? In this episode, we are gonna code our own encryption library. It is loosely based on the ARC4 cipher, but with some improvements which makes it more secure. We're gonna expose a couple of functions from our library, and it's an initialization function which takes a key as an argument. There's a encrypt function and there's a decrypt function, and finally an uninitialization function. So it's very easy to use, and let's get started. Hello everyone, and welcome to today's show. Today we're going to code our very own encryption library using the ARC4 algorithm. When talking about encryption, that is one of the more easy encryption ciphers to implement. But it's a little bit bigger project than we usually do, so I will not be coding inside of the terminal today. I will do most of the work through VS Code. So let's begin by launching the Sociopath SCP client, so we will be able to code live against the server. I will just go into I will put it in my temporary directory, and I will create a new directory, and I will call this ARC4, spelled like this. So the algorithm is written like this, RC4, but it's pronounced ARC4, so I think that's a good name for the library. So I will simply create an empty folder, and I'll right click and open an editor. Then I will have access to the entire folder inside of VS Code, like so. And I will minimize my Sociopath and close down this. And I will also log into my server and attach to my screen, or I will create a new screen instead. And I will configure it, and as you run command VBell off, and as usual I will write a simple bash script like this, just so I don't accidentally close down this window and terminate the screen. So let's go into my temp directory and go into my ARC4, and here we are, an empty folder. So what do we need? I will create two files, or three actually. First I will have the actual code, the arc4.c, like so. And as I save, we can see here it's successfully updated to the server. And we will also need a arc4.h for our structures and includes and definitions and macros and such. And to make our life a little bit easier, I will also create a make file, which is going to compile the whole thing. And actually, I will create a fourth file as well. This is just a temporary file. We won't need this file when the project is completed. but as we are implementing this encryption, it will be easier if we have an example program which we can use to try things out. And I will call this example.c, because we are creating a shared library. So this library will be used by different C projects, and that means that the arc4.c file will not have a main function. So this example.c will provide our temporary main function so we can run it. Alright, so in the make file I will simply define the stuff that needs to be compiled. So the first thing will be arc4.o, and you write it like this. So the file that's the target, and then a colon, and then you write the dependencies. So this file will depend on arc4.c, like so. And then you tab and you write the command. So I will do gcc-c arc4.c, like this. And I will also turn on optimizations at the highest level, as well as log messages. And when that file has compiled successfully, we will have an arc4.o, and then we will create the actual arc4 library. So this depends on arc4.o, and I can't really remember how to let's see, all the flags necessary to create the shared library. So I will check how I did it in my Toralizer make file. And I will simply copy this part right here. So I will do gcc, and we are compiling arc4.o, or linking actually, and the output will be called arc4.so. That's the extension for a shared library, and we want the optimizations and the login, and then this additional flags necessary for a shared library. Okay. There we go. So after those two steps, our library is compiled, but I will also have the example .o dependent on example.c, gcc-c example.c, and I will turn on optimizations and wall. And when we have the object file, we can compile example, which will need example.o, And then we simply do gcc example.o -o example wall 02. And I will also create a clean, which simply removes everything besides the source files. So all O files, all SO files, as well as the example binary executable. And then I will just tell the makefile what we should do as a default when we run the command. And I want to compile arc4 and example. So this is our makefile. If I didn't miss anything, I think we should be able to, let's just go into the temp and the arc4, and I will set this to my home so the prompt won't be so big like this. And I didn't save the .h file, I think, and the example and the make file. There we go, arc4, makefile, arc4.h, and example. So I should be able to run the make now. And we get a reference error for the main, but the .o file should have been created. Yes, they did. So everything seems to be working. Even the SO file did be created, even though everything is just empty source files. And if we do make clean, we're back to where we started. Okay, that's a little bit of administrative work, but it will pay off when we need to recompile and debug our code. I'll close down the makefile because we don't need to do much with that. And I will actually start with the example file because if we create the example first, then we have a kind of a roadmap to the different functions that we need to create later on. So I think that's a rather good way to start. I'm gonna include the arc4.h, arc4.h, and inside that I will have my regular definitions. So I usually start by putting in the stdio. That will be removed later on because we're not going to use any of these libraries, but during development I think it's easier to have all the usual standard libraries ready to go. Like so. Okay, so how will this example file work? I'm gonna start by just creating function definitions. So we do everything in the order that you should, even though this is a small file. So we'll have an int main with no arguments, And that'll be all for now. So I'll create the actual main. And I never seem to learn where to find my curly braces on my Mac. Alright, here they are. So I will make this file a little sloppy and easy to work with, because will not be a part of our production code, so to speak. So I will just do it as easy as it can be for myself. So I'm going to create a couple of pointers. I will have one for the key, and I'll have one for the source text that we want to encrypt. I will have one for the destination text, and I will have one additional pointer for when we decrypt the encrypted text. So let's call this encrypted instead, and this decrypted. That's a little bit more obvious. And I think I need to make this a little bit smaller. I hope that won't be a problem for you. Okay, and I will just define this statically. So I will set the key to, let's see, something easy like tomatoes. When you run this code for real, you should always create a real encryption key. So this can really be anywhere from 8 bits to 2048 bits, according to the standard. But this will do as an example. And the text I want to encrypt is a part of a Shakespeare poem. Shall I compare thee to a summer's day? Okay. We will also need to, before we do that, I need to define a couple of type definitions, because I'll be using 8 bits integers, and I will use 32 bits and possibly 16. So I'm going to define those first. So let's define we will do unsigned char, that is an 8-bit value, and I will call this int 8. Not defined, by the way. This should be a type definition. So a type definition is when you create your own type. Everything you write is what the source name is, and the last one is the destination. Okay, so the next type definition will be a 16-bit int, and that is defined in C as an unsigned short int. And I will call it int60. And finally, we need an 8-bit variable as well, and I will type this as an unsigned char int 8. Oh, sorry, I have done that already. The only thing we have left is a regular 32-bit integer. and that will be a regular unsigned int like this. Okay, so now we have our type definitions, and let's continue with the example main function. So we have the string that we want to encrypt, we have the key, we will also have a pointer to a structure, which I will call arc4, and I will call this pointer arc4 like this. So this will contain the internal state of the encryption engine, so to speak. And I will define this as a, let's do it here. I will do struct s. I usually prefix my structures with an s. That's a stylistic choice though. So s arc4, and what will this contain? Well, we will actually use the Wikipedia page. It's a very good Wikipedia page which tells exactly how to implement this encryption. Not in a specific language like C, but with pseudocode. Okay, so we have this, and now that we have the key, by the way, we also need two size variables. So let's do int 16, and what do we need? We need two size variables. So let's call those size key and size text. And I will just use this string length to define those. So s key equals strlen key, and s text equals strlen from. Okay, so now I have all that I need in order to call the first arc4 function, and that is called, let me do the function declaration. It will be called arc4 init, because it initializes the arc4 structure. So this will be of type arc4 pointer, and it will take two arguments. It will take a key. Let's do it like this. Unsigned char. No. Let's use our int 8. It's not really an integer because this is a string, but every character is an integer, so it will be okay, I think. So int 8 key int 8, because if I don't do it like this, if I do sometimes char and sometimes int 8, and then I will probably get this signed wrong, and I don't want that. And we will have an int 16 for the size of the key. And I don't need those. Int 8 pointer, int 16, right? Then we go back here and we will set our arc4 equal to arc4 init, and we send our key and our S key. Like so. And this is a function that might fail, but that's very unusual, so I won't care for that during this example program. But if you write a real production grade program, check if this arc4 returns 0, because in that case the malloc returned error. Otherwise we will get one of these structures back and then we are ready to encrypt. Let's add some prints as well. So initializing encryption, and I want to have a way of putting this to the screen instantly. So I will create a definition which I will call F, and I'm not putting this into the arc4.h because this is not something I need in the actual end result in code. This is just for convenience. So F will be F flush std out, and that basically flushes the standard output buffer, so that if I do a printf like this, which is not ending in a new line, it will. And if this takes a couple of seconds to initialize, then this text will not be printed before this delay, which kind of defeats the purpose. So I will put the F right after, like this. And then down new line. Okay. And then let's print out the input first. So I will put it in single quotes. And let's do it like this: a new line and then an arrow. And this is the from text, like so. Then we do the actual encryption. So we will use our encrypted variable. So encrypted equals arc4. Let's define this first. So this will return a string pointer. But I will call it an int 8 pointer, and it will be called arc4 encrypt, and it will take two arguments, one which would be an int8 pointer, so the string that we want to encrypt, and a size in the form of an 16-bit integer, like so. Pretty similar to the initialize function. And the arg4 encryption works like this. You don't need a specific decryption function, because if you try to encrypt the encrypted text, it will be decrypted. So then it goes backwards. So with that in mind, we can just create a macro which will be called arg4 decrypt with two arguments, x and y. And this will just call arg4 encrypt with x and y. So it's not really necessary, but it makes it a little easier to use. And in order to make this encryption function work, we need another function called arg4byte, which produces one single character of encrypted text. So this will be an int8 and not a pointer, just a value. Now that we have our data types and our function declarations done, we can continue with the example.c file. So the encrypted variable will be equal to arg4 encrypt, and we will send in the from text, and we will also send in the size of the text, like so. And this is a function which shouldn't be able to fail, which means that the encrypted variable will now contain the ciphertext. The next thing we need to do is create a function which will make it possible to output the encrypted text in some format, because the encrypted text will not be printable characters. It will be any number of different integer values. And I'm thinking about using an output like this. So 1 byte will be represented by 2 hexadecimal characters, like this. So this is 1 byte, and then 2 bytes per group, and each group will be separated by a space. Okay, so this function will not be a part of the library itself, only this example file. So it shouldn't return anything, and let's call it print bin, because it's binary data. And it will take in an int8 array pointer. Let's call this text. It's not really text, but whatever. And then we will have an int16 for the size, like this. And all we need to do is iterate through the text and print those bytes 2 at a time. So how do we do that in the easiest possible way? There are several approaches, but I think I will just create an int32 as an iterator, and I will have an int8 pointer as well. And I need to assert that size is bigger than 0. And what is assert? Assert is a function which checks if this predicate function is true, and if this is not true, the whole program halts. So it's quite good to use in situations like this, both in this example file, because it's easy and it doesn't matter really if the program exits, and we can also use it in our production code in some places, because we are coding a library and the programmer should send the right arguments. If not, the program should halt, I think. Alright, so we need to go into this arc4 and include what's its name? It's assert.age. And in order to get all the functionality, we also need to include rnumber.h, like this. Now we'll jump down a little bit, same here. Okay, so we know that we have an input which is, let's call it input instead. That we have an input which is, which contains something. Length is bigger than 0. Okay, so let's do a loop then. So for, and we will do, let's make this an int16 instead. That will work better together with this 16-bit size. So let's, and I want to make this const as well. Same here. No. Okay, so let's set I to size and P to input. We're gonna continue the loop as long as I is positive. So I'll just put I here, because it will decrease every iteration, and it will after a while go down to 0 and the loop ends. And the P pointer will instead increase every iteration. Okay, so if, let's see, I need to check something out. So the first iteration, then let's say we have a string which is 32 bytes. So I will be equal to 32, and we will output to 1 byte of data, then it will be equal to 31, and we will output 2 more. So let's see. I think we could write it like this. So if I plus 1, let's see. If I plus 1 modulus 2, if that statement is negative, so it's equal to 0, in that case I want to printf space, and in any case I will print out a hexadecimal value with two digits, and this is what we want to print out. I think this will be correct. So this basically means that if we are even, so if I plus 1 is even, then we will put the space. And we will also use our macro f, so it will print this. No, we don't need that, by the way, because we will end this with a new line anyway, so that will flush the buffer. This should be all, I think, unless I have forgotten something, but let's try it out. So what can we try it out on? We don't have all these functions yet. So let's comment this out, and this as well, and this is okay. And what shall we print as an example? We can print the key. So print bin, that's actually not binary data, but it will work the same. So we will print the key, and S key is the size. Return 0. Something like that. Let's see if this compiles, or if we need to remove something else. Make a lot of warnings. Type def unsigned sure expected before unsigned. for unsigned. I have an empty struct, that's probably it. Let's just put something temporary here then. Type def unsigned. Maybe it is because of the position. Sometimes you need to do one thing before the other, etc. Forgot to end the struct with a semicolon. Is it still complaining? Type def unsigned char int 8. Type def. If we add our type def for our struct, does that error as well? Type def struct as arc4. It's not uploading. Okay, I got disconnected. One good thing with the sociopath is that if you reconnect like this, you don't have to do anything else. It remembers and continues to serve all of your files. So that's good. Okay, let's say this again. And this one. And let's jump down a bit, clear the screen, and let's make it again. Okay, finally. Pointer targets in passing, argument 1 of print bin, differ in signedness. Okay. So this is what happens if I don't use my int 8 everywhere. So where did I not? Here. Let's just change it to int 8 and everything should be okay. Okay, we're down to one screen of errors and warnings. Almost. Does it still? Seems like it needs a typecast because the strings are generally not like these static strings inside of the code. They are generally not unsigned. So let's do a typecast int 8 pointer, and same here, int 8 pointer. So strlen needs it as well. I could just make these strings signed, but then I would have the same problem in the other end instead, because the encryption standard requires them to be unsigned. So let's just typecast this as well, int 8 like so. Do we use them anywhere else except our own functions? Printf shouldn't care, right? Let's do it just for the sake of it. Int 8 like this. Okay. Let's try it again. At least we have very clear and precise error messages in C. Did I go too far? Make clean make. S key equals S. Didn't I save? Save. Why does it... Okay, it's higher up in the code. Right. Int 8 star. And there we have it. Okay. That should be all right. Make clean, jump down, make. What does it say this time? Pointer targets in passing argument 1 of string length, difference, different. I did it in the wrong direction. Okay. That's kind of funny. So instead of int 8 here, let's see. There, and there. We should just have char, because we have them as int 8, but the functions we're calling requires them to be regular strings. So assign char pointer. Okay, this time it should look a little bit better, I think. Make clean, jump down a bit and make. Warning, pointer target in assignment from char to int 8, aka unsigned, different sign does. So it doesn't seem to be enough by doing it this way. Okay, let's do it the other way then. I will undo until I see this change, like so. So now all of these are okay, and this will probably not be, but here we can do a conversion in the other direction instead. And that should be all. Make, clean, jump down, make. Okay, now we're talking. Warning, unused variable. That's an annoying message. If I don't want to use my variables, I don't use my variables. But okay, so let's do something like key equals from equals encrypted equals decrypted equals key equals 0. Is that enough? Maybe I should end it with a semicolon. Operation on key may be undefined. Variable as text set but not used. Right. So it wasn't enough to mention the key twice. This is only set and all of these are used. So we need a key. What about from equals key? Okay, now what? S text. But that's an int, right? Yeah, I haven't used that yet because we haven't gotten that far. These are only warnings, by the way, but when I try out my code, I want to remove everything of the sort. So which is this? This is the S text. So we will change the key later on. Let's just do S key equals S text equals 0. Now it should be completely warning free, I believe. No, one more. Warning, unused variable arg4. Okay, I haven't used that. I can just comment that out for now. Make, clean, make. Okay, finally. Let's see if this works as intended. Example. Okay, so shall I compare the to summer's day, and then I am showing some of the key, but I am showing half a group here and half a group here. What will happen if where is it? If I just do I here. Okay, now it looks good. It prints out in hexadecimal characters a nice formatted group. Very nice. That means we can begin with the actual encryption code now. Finally. So let's go over to the arc4.h and begin working on our structure. This will contain the internal state of the encryption engine, so to speak. So let's go to that wonderful Wikipedia article. So arc4 wiki, and I want the English speaking Wikipedia. And let's hide this and make it a little bit bigger for you guys. And let's do something like this. Let's use the whole screen. I will probably be looking at this anyway. So there's a lot of text here, and some of it are warnings that this encryption standard isn't secure. But I have read through all of that, and I'm not sure if I agree, actually. Well, the thing is, they claim that the output of the encryption is distinguishable when compared to purely random bytes of data. And that could be potentially be used to backtrack and crack the encryption. And it has indeed been used. For example, the Wi-Fi encryption standard WEP used exactly this encryption with very small keys and a special kind of seeding algorithm, which they were able to crack it in the wild in a couple of seconds. But that's only in combination with the WEP technology. And there has been some talk that in combination with the TLS, the encryption standard on the web, it's also not safe, and it's not safe the first couple of bytes which it produces is not safe. So, since we are using this encryption firsthand in our own code, not together with anything else, and I will also create a mechanism which will disregard the first 500 million output bytes, which will stop all the other cracking techniques. So I think with a big enough key, which is randomized in a secure manner, I think arc4 is still secure. Okay, so you don't need to read through the whole shebang, but those gray information boxes are very good. So there's two steps. Step one is what I call the initialization of the crypto. That's when you only take the key and you prepare the internal state of the encryption engine. And this is what you do. And then the next stage, which happens every time you need to encrypt 1 byte, or more exactly, produce 1 byte of key stream data. So then you do this. So let's start writing. No, let's begin by creating our arc4 struct. I will zoom in here a little bit, not that much. temporarily so we can have both on the same page. So if we look through this, what do we need? We need an 32-bit, or we need an 8-bit int, which will go from 0 to 255. We will need an array called S, which will be consisted of 8 bits values and 256 of them. Then we have the J value, same as I, 1 int, 8. And then we have the key. And that's basically it. So let's summarize. We need int I, int 8, I, j, and later on we will need a k, so I'll put it here. And then we will need the array, so int 8, s, and 256 of them. So we have I, we have j, we have the k, and we have the s. Do we need anything more down here? We need temporary variables as well, but I won't put them in the struct. So, okay, this is all we need for our own structure. So let's begin writing on our initialization function. And this will, let's copy this whole thing. And let's include our, arc4.h. There's something weird going on with the caps lock. Include arc4.h. I wonder if you can disable the caps lock. I never use it anyway. I use shift. Okay, let's see. Include arc4.h, and then we will do the initialization function. So it will return an arc4 structure pointer. And the first argument is the key. The second is the size of the key, like so. And the first thing we need to do is allocate space for the actual structure. So I will create a pointer for that. I'll just call it P because we're going to reference it quite a lot. And P should be equal to malloc, and it should be the size of struct S arc4. So the size of our struct, that many bytes of memory we shall allocate. And here I will do an if clause. So let me just check the return values for malloc. Man2, no, man3 malloc. So I know it returns the memory address, but if it fails, return value. They return null and they set error num. Okay, so let's just do something like assert p error number. Then it will check if this has errored out, and if so, display an error message and quit. Because if you can't allocate memory for our structure, there's no point in continuing the show. Okay. So now that we have allocated our structure, now I will just do this. And I will work in the following manner. Let's close this down and change up the size a little bit. And then I will paste this in and make block comments out of it. I think it's command this or control this. Let's do something like this instead. Annoying. I never seem to learn VS Code for Mac. I know all of these different things on my PC, but it's not the same on my Mac. Well, this works too. Okay, so now I have in the comments what needs to be done, and then I will just do it. But before we begin, I want to zero out all the state variables. So let's do something like no, let's just do a simple thing. Int 8 x and 4 x equals 0, x less than 256, x plus plus, and we want to take the PS, so that is the this array. I want to zero that out. So PS of x equals 0, and then I'll just do PI equals PJ equals PK equals 0. I like starting from 0 instead of randomness. Okay, so the first thing is this loop right here. We'll iterate through 0 to 255 with this I variable, and we will set s of I to I. Pretty simple stuff. The code will look kinda difficult though, but it really isn't. Why is this not? Oh, never mind. Okay, so for P I equals 0 and P I less than 256, P I plus plus, and P S of I equals I. Okay, this is done. So if we do one thing at a time, it's quite simple to do this actually. Can't say that for every crypto. And then we will set J to 0, but we have done that already. So we will jump into this loop and we will let the I variable do another identical for loop. So let's just copy this line. Like this. And what will happen then? We need two temporary variables as well, by the way. So we need int 8, I will call them temp1 and temp2. And I want to zero them as well from the beginning. So let's just do temp1 equals temp2 equals 0, like so. Okay, so what will happen inside of this loop? Let's remove the things we have done already. Okay, so this is a rather difficult line. I want to break them down. So what's the first thing that happens right here? Well, the parentheses is evaluated first. So let's set, let me see, key I mod key length. Actually, let's evaluate this first. I mod key length. So temp1 will be equal to key. So it will be key of I no, where am I? We are here, right? So I mod key length. So P arrow I modulus key length. So that's the size. Okay, so this part is okay. Now we can take the rest of this parentheses one at a time. So P J no temp2 equals pj plus ps of I plus key of, and then the stuff we evaluated right here. So key temp1. And then we will set pj. So now we are doing this part. So pj should be equal to everything in this parenthesis, which was temp2, and mod 256. Modulus 256. Like this. And finally we should swap the values of s of I and s of j. So let's set temp1 to ps of I. No, not just I. We need to change those occurrences to pi. And pi. There's a lot that can go wrong here, as you can see. You need to be very precise. So temp1, and that is why I could do everything in one line if I want to, but it's very error prone, and that's why I break it down with these temporary variables. So temp1 is equal to PSPI, and temp2 is equal to PSPJ, and then we will just swap them. So PS of PI equals, and here we see that temp2 equals this. No, temp1 equals this that I'm working with now, which means it should be equal to temp2 instead. And then we have PS of PJ which is currently equal to temp2, and it should be equal to temp1. And that's it. The code is very difficult to read, but it's quite simple, and it's quite easy to follow it step by step if you break it down into smaller steps. And that is basically it. I'm gonna do one more thing though, because if we go back to the Wikipedia page and we go to the next step, we see that they zero out I and j, and then they have an endless loop which happens every time you encrypt a character. So we have a function which encrypts a character, which means we only have to worry about this. But this part we should put here in the initialization function, because then we can just do several consecutive calls to our arc4byte function. So P of I equals P of j equals 0. like so. And then we just return P. I think we did it right. If we go back here and we remove this line and put this line back, then we can print, instead of printing the key, let's print arc4 S. So the initial state of the encryption engine, and I will put one of these on top as well, so we may see the difference. No, sorry, can't do that. We haven't initialized it yet. But okay, let's see what happens. Clear, jump down a bit, make clean, and make. Okay, couple of errors. If we go to the very beginning, warning suggest parentheses around assignment used as truth value. Well, I want to use it as a truth value. I don't really care for warnings like this. If I want to code it this way, I will code it that way. Implicit declaration of function assert P error, okay. And here I forgot something. And arc4 has no member named S, okay. So a couple of small typos. If we begin in the H file, I guess this is the problem. Is this a big S or small s? It is a small s, so why doesn't it have a member called S? Did I perhaps arc4 P? That's weird. Maybe it's something because of this. We should check if X is less than 256. So that was an easy one. And what else? Assert P error. Where is that located? Man3 assert P error. Okay, I need this GNU source thingy. Let's try it again. Make clean, jump down a bit, clear, and make. Boom. Okay. Int 8, IJK, unknown type name. Unknown type name, int 8. I put this before these. Let's move them. Like so. I don't like I have to break this up, but what can you do? This is just a warning. Error I undeclared. Okay, I missed one. Line 18. Wrong file. 18. So this should be PI, and this should also be PI. Okay. What now? Error arc for undeclared. No, the problem must be higher than that. Arc for undeclared in example. And pointer targets in passing. Arc for init key. Char star. That's weird. Didn't I use my int8 for that function declaration? Let's check it out. So int8 key and int8. It's weird. Let's put this back, by the way. And okay, it's this function. int8 input. In16. Well, where is it? Let's check it out again. So, expected int 8, arc for init key. Pointer targets in passing argument 1 of arc for init differ in signedness, because this is a char. int8 key. So key is a char. Okay, let's typecast it then. Where do we have it? Right here, okay. So it's currently a, let's see, it should be an int8 pointer, like so. Okay, let's see what we have. Still a warning about this one, but that's nothing we can do anything about. Undefined reference to arc4 init. We need to link that one. Let's just, no. So go into the make file, and then we will do let's make it easy. I will just do arc4.so as one of the input arguments. So make clean, clear, jump down a bit, make, and now it still doesn't compile. Undefined reference to arc4 init. What did it run? GCC arc4.so. Arc4 init. Do I include it in the header file? Include arc4.h. Include arc4.h. arc4 init. Undefined reference. Okay, for the time being, let's cheat a little bit. I will fix this later on. I don't have the patience right now. So I'm gonna go and when we compile final program, we do arc4.o instead. Like so. Okay, this time it worked. We probably need to explicitly export the functions when we use the shared library. I will dig into that in a little bit, but now we do have ourselves a binary. So let's try it out. That doesn't look very good. Let's do ltrace-f malloc arnom location. Let's try the strace. Right, initializing encryption. How did I write that if clause, by the way? Maybe I reversed the conditions. Let's see. If p malloc. Okay, this should be the other way around. So if p. Alright. Make clean, clear, make, and we'll run example. Did it remove everything when I did make clean? arc4chc. Yes. So how come it freezes there? Malloc size of struct s arc4. If that is 0, assert p error. For x equals 0, x less than 256. I think that 0 means that it's some weird number format. Make Okay, no errors at all, no warnings even. But the same outcome. What is this? Do we have an endless loop on our hands? That's probably the only possible thing, right? So pi equals 0, while pi is less than 256. Maybe we should do this with a little bit bigger structure. These could be int 16s instead. We're probably overflowing that 8-bit variable. So that wasn't the case. For x equals 0, and what is x? X is also an int 8. So that should be the same problem then. Right. There we go, finally. Okay, so this is part of the internal state of the encryption. Okay, so the next thing we need to do, that is creating the arc4 byte function, which will create one single byte of the key stream. And the key stream is what we will use to encrypt and to decrypt stuff. So let's begin. I will have int 16s with temp1 and temp2, just like before. And we do need an argument, by the way. We need to attach the structure. So let's alter this and put in the arc4 star, so we can have access to the internal state of the encryption. And just like before, I will go to the Wikipedia page, and this time I will copy this part. So in this pseudocode right here, they use a while loop, and they loop as long as it's generating output. But we'll not do it like that. Instead, this function will be called each time we will produce 1 byte. So we don't need this loop. That will be handled in the encryption function. So let's do it like before and take one line at a time. So we will do pi equals, and then pi plus 1, and we mod it with 256. First one is done. Then we do similar with the J part. So PJ equals PJ plus PS of PI. So we just replace the variables with our variables inside of the structure. And we mod this with 256, just like before. Okay. Then we will swap the values. So this is like we did previously with the initialization function. So I will let temp1 equal PS of PI, and temp2 will equal PS of PJ, like so. And then I will just I missed the S right here. And then I will just do PS of PI equals something, and PS of PJ PS of PI PS of PJ equals something. Okay, so temp2 equals the J part, which means it should equal the I part now. So this equals temp2, and the PJ should equal temp1, like this. And then this one is done as well. Why did it mess up the indentation? Never mind. Okay, and then we have this T variable. That is their version of our temporary variables. So we'll just continue as before. So temp1 equals, in the parentheses, PS of PI. So this is not really a spectator sport. I hope you don't find this too boring, but we're almost done. Plus PS of PJ, and then we mod it with 256. And then we use the K variable for the first time. So P.K equals PS of temp1. And this is the final output byte, as we can see right here. So let's take care of these indentations. and then at the end we just return pk, like this. And then we have our arc for byte function, which is the most important in this entire project. So the next step will be to implement the arc for encrypt, and this is quite straightforward to do now that we have a arc for byte function. So let's see, we need one more argument. We need to include the arc for structure. So, or do we? Yes, we do. Arc for star. And we go here and do arc for p and int 8. This will be the what shall we call it? The thing we need to encrypt, the clear text. Let's call it CT for clear text. And int 16, this is the size of the clear text that we want to create. And we'll return this as a as a char buffer, a regular string actually. So let's create a int 16 which will hold the amount of memory we need to allocate. So let's call this mem size, and we will need exactly as much memory as this size plus 1. Okay, so we don't really need to, because when you encrypt something, if we encrypt ABC, the resulting ciphertext will be something like this. It will be the same number of characters, which makes it quite convenient for us. We don't need this variable. Instead, we'll just do, let's create a variable first. So let's call this ciphertext. And let's call this clear text, because both will abbreviate to CT, and we can't mix those. So int 8 ciphertext, and ciphertext will be equal to int 8 malloc, and we want size plus 1. Size should be enough really, but I like allocating one more just in case. We will also need something we can use as a counter. Let's call this int 16x. We will do a for loop where we set x equal to 0 and we're gonna loop as long as x is less than the size and x++. And what are we gonna do at each iteration? Let's create a, let me see, we need this and that. Okay, let's do it like this. So the ciphertext of x will be equal to the clear text of x, and then we take this symbol, and some people usually mix this up with the power of, but this little symbol in C means XOR. So XOR is a binary function, like if you have two zeros, the result will be 0. If you have 1, 0 and 1, 1 and a 1, the result will be 1. If you have a 0 and a 1, so the other way around, it will also be 1. And finally, if you have two zeros, it will be 0. So that is what XOR is. It's usually used in conjunction with the key stream that a stream cipher like ARC4 produces. So here we will just call ARC4 byte with our P, and that will return 1 byte of key stream, which we will XOR with a clear text, and that will produce the ciphertext. And let's do an error check here as well. So if ciphertext is 0, then we want to assert p error r number, like so. And if everything goes well, we will simply return our new buffer ciphertext. Quite simple, straightforward encryption function. And we need a decryption as well, but that we have already defined because it's the same function, just that we give it the ciphertext instead of the clear text. And the key is the same, so basically this part is the same. Okay, so that is done as well. And before I forget, let's see, encrypted equals ARC4. So we can take this back now, and we encrypt the clear text, and we print out the encrypted. Sorry, this should be the size of the text. This should be the encrypted, because this time we don't want to check the S variable in the structure. We want to see the actual encrypted text. Yes. Okay, so after we have printed the text, what do? Do we just use the decryption function? No, we can't do that, because in order for everything to be the same, we must uninitialize the arc4, and we need to reinitialize it with a key again. So we start everything from scratch, and then we can start to decrypt. Otherwise it won't work. So let's create our uninit function as well, and that can be a void arc4. Let's make it easy for us for the time being, because there's only one thing we need to do at the moment when we uninitialize, and that is to free the memory allocation. So let's define arc4 uninit of x as free x. I will also need to find, let me just do a fast googling after export C shared library function, because there's a special string we need to use to export the functions. Let's see. This one. So let's make a definition. We define a keyword named export, and it will be the same as this. So all the functions that we want to export, like the arc4byte function, we don't need to export that, because the end user will only use the encrypt and decrypt functions and the init. So we put export for this and before this, save, and we need to do the same here. So export, and not this one, but this one. Export. Like so. Okay, so that is done as well. Now we may continue our example. So we have printed the encrypted strings. Now we're gonna uninitialize. So we do arc4 uninit on the arc4 pointer. Then we repeat some of the steps like before. So let's copy this part for init. There we go. And let's create another one of these. Encrypted. So I will copy this part. Look for init. Okay, something like this. And let's put the arrow 1, 2, 1, 2 like this instead. Okay, so we initialize and we need to change the order of these. Because we need to decrypt this first. So it's initialized. Now we will create our decrypted. So decrypted equals, and we will use the decrypt function, but as you know, it's the same. The only thing we're going to change is the from. Here we had the clear text before. Now we will do the ciphertext, which we get from this encrypted call. So where were we? Decrypted equals, and this should be encrypted, and everything else is the same, and this should be decrypted as well. And then we don't need to print the binary. Okay, so if we have done everything correct, then the decrypted text should be exactly the same as what we had from the beginning. So we take the text, we encrypt it, and we decrypt it back to the start, so to say. Okay, let's save, and we make clean, jump down, we clear, and we do make. Okay, not a lot of errors and warnings. Let's start from the beginning. Error T undefined. Size plus T. Text 54 in arc4.c. 54 ciphertext size plus T plus 1 should be plus 1. Okay, we got more errors. Let's do make clean first. Make. Okay. Warning, this for clause does not guard for x equals 0 while x is less than size x plus plus. X equals 0, x is less than size x plus plus. That shouldn't be a problem. This state doesn't guard this statement and return ciphertext. But the ladder is misleadingly indented. Okay, so it even checks my indentation thing. But sometimes that's good, actually. I have corrected errors in the past because of that. So let's see what it says. Okay, it's this part. Let's move it here. We make clean, we go down, and we clear, and we make again. Okay, passing argument 1 of arc for encrypt from incompatible pointer type. Arc for encrypt from. Okay. Let's see. Arc for encrypt from. Encrypted equals arc for encrypt from. And from is set to this. Okay, we probably need to typecast this then. But it worked before, right? Oh, never mind. int 8 star. Let's do it like that. Do we have any more occurrences of the same? Decrypted. No. Okay, let's try again. Make clean. And make. Arc for encrypt from incompatible pointer type. Encrypted equals. Wait a second. I forgot to attach the structure. Right? We did change the signature of that function. So, where were we? Arc for encrypt. The first argument should be the arc for, like this. And same with the decrypt. So, arc for. And we need to add a variable to the macro as well. So x, y, z, x, y, z. Like so. Let's try again. Make, clean, clear, and we make. And we have this signedness problem again. So encrypted equals arc for encrypt. Arc for encrypt. So let's see. So encrypted, how did we declare encrypted? Okay, let's move this to its own instead. Decrypted. Decrypted as well, I think. So int 8 encrypted, decrypted. And we make clean, and we clear, and we make. Okay, almost there. Another, okay, that's our temporary assignment. We don't even need that anymore. So let's just remove this part and this as well. Save, make clean, clear, and we make. Okay, it compiled. Let's see what happens. Okay, initializing encryption done, and then it shows the string that we want to encrypt, and it shows the hexadecimal version of the encrypted text. Then we reinitialize, we feed it with the ciphertext, and we end up with the same string as we had from the beginning. So everything works. The only thing we should add to this, that is remember when I talked about that some people think that the ARC4 encryption is not safe. One of the biggest concerns was that the first thousands of or millions of bytes is not good enough, so to speak. So we need, when we initialize, we need to, I call it to whitewash. We need to whitewash away the first 50 or 500 million of these. Yeah. So let's go into our encryption function. No, our initialization function. This one. And I want to create an int32, which I'm going to use as I'm going to use it for a for loop, basically. I don't really want to call it I, because that makes it interchangeable with this pi. So let's just call this C for count, N for number. N is good. And let's go into the let's see, ARC4, and we create a macro for this. So we define ARC4 whitewash, and we need we don't need an argument actually. And what we're gonna do, by the way, we do need an argument. Let's take the variable for the loop as an argument. So the only thing this macro will do is a for loop where we go from x equals 0 while x is less than let's call it whitewash count, or whitewash, let's call it m's. So these are millions of iterations. So x is less than ms times 1, 1, 2, 3, 1, 2, 3. And I plus plus. And the only thing we need to do is, okay, we need one argument more. The only thing we're gonna do, let's do it on the next line. We will call arc4 byte with the structure or a pointer of the structure as an argument. So basically that. We will call this, which it will generate a byte, and each time it loops it will do that. But we're not going to do anything with that byte, because all we need to do is getting ahead in the in the state, so to speak. But if we do it like this, then GCC will recognize that it's redundant, and it will, as part of the optimization, it will just remove this. So we will need to typecast this to something called volatile int8, like so. And that basically means, in this context, that the GCC should not optimize it. Okay, so let's put this as part of our initialization. So when we are done with the rest of the initialization steps, at the end here we will simply call the arc4 whitewash and specify our variable for the iterations and the name of our structure, which is P, like this. Okay, and if this works, we should see that it takes longer when we run this initialization, a couple of seconds. We also need to define the m's. So how many million iterations should we have? And I want 500 million. I think that ought to do it. If you think it takes too long when you run this, try changing this to 250 or 100, because I have a quite fast CPU, so this should go quite fast. And we save everything, and hopefully we haven't introduced any additional errors. Make clean, and we clear, and we make. Yes, we did. Okay. What does it say? Okay, I++. That's wrong. Where were we? Here. So it should say X++, right? Alright, let's try it again. Make clean, go down a bit, and we clear, and we make. It compiled. Let's run it. Initializing. And as you can see, it takes a couple of steps, and then it does the same as it did before. Only this time it's probably safe. As long as we have a really good encryption key, which we don't at the moment. At the moment we only have, in this example at least, we only have the word tomatoes. We should randomize a 2048 bits key if we were to use this in the wild. But everything works exactly as we intended it to. So we have successfully implemented the arc4 crypto, and we have turned it into our very own library, which can be shared between different applications. And when I create a project for transferring and encrypting files, I will use this library for that. So then I will show you how to use this library in your code. But I hope you enjoyed this, and don't forget to subscribe if you like this and want to see more. There is a lot of advanced C videos coming forward. So don't miss out and stay tuned. Thanks for watching and thanks for today. The first thing I want to do before we start with the actual encryption tool is we need to install the library. So how do we install our own library? Well, let's go into our directory and let's alter our makefile a little bit. So if you remember, the ultimate target of this makefile is to create this arc4.so. However, I'm gonna rename it to libarc4so because it will be easier to use it if it has the correct naming standard. I will also have to check what the correct library directory is. Before it was always userlib, but now, at least on my 64-bit Linux system, it is this one. So you need to add this x86, etc. So let's grab this and we also need the include directory, but that's just user include as usual, I think. User include arc. Yeah. So let's create two variables. One which is going to be the encryptor, and I will put user include. That's where we put the H files, and then libdir. That's where we put the library file. So when we have compiled libarc4.so, then we will copy libarc4.so to the, let's see, the libdir. And we're gonna copy the arc4.h to our encryptor, like so. And then we're gonna run the command ldconfig, which will update all the configuration files necessary for the library to work. Okay, let's try it. And we need to run this as root because we don't have write permission to that directory. So let's begin by doing make clean. And okay, by the way, it will be better if we create a new target which we'll call install. And let's grab these 3 lines and put them here instead. So in this arc4 we compile the actual library, and then we do make install as its own command to install it. So make clean, let me just clear. So make clean and then make, and finally sudo make install. Okay, no errors. So let's go to the directory for today's program. I'm gonna call it FSE, and I'm not gonna tell what the FS stands for, but the E stands for encrypt, and that's because I don't want to spoil what the ultimate end with this project is, and I'm gonna tell that in a later episode. So let's create a test file, test.c, and we will include just the standard IO, and we're going to include our own arc4.h, and we use these angle brackets because now it is installed globally on the system. And then I'm going to just create an empty main which returns 0. So basically I just want to see if it compiles. Okay, we need to let's run one of the functions in that library. So what do we have? We have arc. Let me just check. So more user include arc4. So let's do arc4 init. It takes the key and the size of the key. That's right. So arc4 init and a key, and the size of the key in bytes, so 5. This should work. And let's cast this to a volatile. So let's cast this to a volatile arc4 pointer, and that's basically just so the compiler won't simply ignore this line because we don't do anything with the return value. Okay, so then we first compile it with the -c, so test.c, and we get the object file. And now when we're going to link, we do gcc test.o-o test, and we if we don't add anything else, we get the error that it doesn't find arc4 init. But this is globally installed on the system, so all we need to do is add -l arc4, and it compiles and runs. Great. So now we have installed our library. Okay guys, let's end there for today, and we will continue this project another day. Don't forget to like and subscribe, and thanks for watching, and thanks for today. Sup guys, welcome to today's show. Today we are gonna answer this question. Why 755? You have probably sometime used the command chmod 755 and the name of a file or a directory. But what does this 755 mean in detail? This and more we're gonna talk about today when we are discussing Linux file system security. And this topic will be divided into the following different things. We are gonna talk about file permissions. And that also is applicative to directories. And is a huge part of the Linux and Unix security. We will also discuss the different targets that you can set these permissions for. And we will also discuss the chmod command in detail, how to use it. And if we have time left, I will also mention the change own command. Plus, I will be teaching how to view permissions as well. So let's start with the different permissions that are available on a Unix and Linux system. So first and foremost, we have read. And read is what it sounds like. If you have the read permission on a file, you can open the file and read its file contents. If you have read permission on a directory, you may list the contents of that directory, all the file names. So read has the character flag of R, and that is important when it comes to the configuring of permissions using the chmod command, and also while viewing the permissions. But there is also a numeric representation of that R flag. So for the read permission, that is number 4. And there is also a binary representation, but I'll get back to that in a little while. Then we have the write permissions, and that is a W as a flag and number 2 in the numeric representation. So what is the write permission? Well, if you have the write permissions on a file, you may edit the file, alter the file contents and save the file. You may also delete the file. And if you have the write permission on a directory, you can do basically anything, almost. You may delete files, you may create files, rename files. But there is also a third very important permission, which is called access. And that has an X in the flag representation and a number 1 in the numeric representation. So, what does access mean? Read and write permissions are quite similar for directories and for files, but access differs quite a lot. So if you have the access permission for a directory, you may enter that directory. You may access the directory. So basically it means you can CD into the directory. If you only have the access and not the read, you may not do ls and show the contents of that directory, but you may access it and you may go to subfolders if you know the name of them. And if you have the access permission on a file, on the other hand, that means that you may execute that file. So executing a file, that's basically when you run a script or when you start a program. So, for example, the ls command is a program. If you have the X flag, you may run the ls command. Otherwise, you'll get a error message saying permission denied. So that is basically it when it comes to permissions. But I also want to talk a little bit about their binary representation. So let me just scroll a little bit. Okay, so why are we talking about binary? That is because I want you to understand how this system is constructed. It's a very, very intelligent system, which are based on those flags. So this kind of flag system is not only used for permissions, it's used for a lot of different things in the Linux operating system, but also in a lot of low-level code like C programming and stuff. And you will soon understand why. Okay, so if we convert the number 1 to binary with 4 digits, we will get 0, 0, 0, 1. Okay? If we convert the 2, we will get 0, 0, 1, 0. And notice that we don't have a 3. We have a 1, we have a 2, and we have a 4. Why is that? Well, if we convert the 4 to binary, then we get 0, 1, 0, 0. So a pattern emerges. What we can do is we draw a line right here and right here, and then we see that all those ones are in different columns, which means that we can combine them as we would like. So let's say we want to combine the read and the write permission. That would be the number 4 plus the number 2 equals 6. So if we give the number 6 when we configure the permissions, it will set both these two flags. And if you use the ls command to check the permissions, then it only needs this 6, because if you look at these three numbers, 1, 2, and 4, the only way to produce a 6 is by using the 4 and the 2. And that is true for all possible combinations of these values. As we can see here, the ones are in their own column. So if we set this, or if we set this, or this, it won't alter these ones. And what does that mean? Well, it means that with one single integer, we can basically store as many flags as we would like, at least up to 4.3 billion or whatever. And we can store all possible combinations of these flags as well in one single integer. And that is a very, very powerful way of storing data. Okay? The next thing we're going to talk about is the targets and the output of the ls command. And let's start by talking a little bit about the targets. Because we have these permissions, read, write, access. But who do we give the permissions? What do we set it on? Well, we have, for every file and every directory, we have 3 different alternatives. We have the owner, and that is also called the user. We have something that is called group, and we have other. And these are kind of self-explanatory. The user, or the owner, that is the owner of the file, basically. So if you have created a file in your home directory, for example, then you are the user or the owner. And that means that you're allowed to change the permissions. If you remove all the permissions, then you cannot open the file. But you may give yourself read-write access and then open the file. You can also delete the file and stuff like that. So you need to decide for every file and every directory if the owner should have read or write or access or any combination of the 3. The same goes along for this group. So every user on a Linux system is a member of at least one group, but possibly several. So basically the administrator, the root on the system, may create those groups. And you can be a part of one group, or you can be a part of thousands. And you can be part of named groups, or simply a numeric representation. If you set permissions for a specific group, then you have endless possibilities. Because if you just have these 3 different levels, the owner, the group, and other is just applicative to those who are not the owner and not a member of any group. So it's a very simple system with small building blocks, but you can create really powerful things with it. And we are going to talk a little bit about the flags of these targets as well. So let me just put them down here again. So the user is the official name for this owner of the file. So I will call it user from now on. But sometimes it's being called the owner as well. And then we have group, and we have other. So it's very easy to remember those flags, because the user has a U, the group has a G, and the other has an O. So when you set the permissions, you have the possibility of using these flags to specify the target. But there is also a combination of all these, which is the A flag. And that basically stands for all. So it alters all these three targets and sets the permissions you specify. Okay, what else? Well, you may also use combinations of these. So if you want to set for the user and the group, you just do UG, or other and group, OG. So easy system, but kind of simple to use anyway. Another thing I'm gonna do is I'm gonna color these different targets. So the user will be yellow in this example, the group will be green, and the other will be purple, or possibly pink. And then I'm gonna zoom out a little bit so we may see everything here. Okay, so if you do the regular ls command, then you will only see the names of the file by default, unless you have changed the default settings by an alias or similar. But if you do like is shown here, ls-al, and this is an L, a small l, not a 1. So ls-al, then you get one line per file or directory, and you get some additional information, like the day it was altered, and the size of the file, and stuff like that. And then we have the names to the right. But the thing that is interesting in this example are these right here. So perhaps you have seen this before but haven't given it much thought. These are the different permissions. And it might, if you look, if you're not familiar with this, it might be difficult to make sense of this, because it's just a lot of different characters, and you may not see any pattern here. But let me do this. If I take my yellow pencil and I highlight this part, and I'll take my green and I'll highlight these, and finally I will take my purple or pink and highlight these. And then I will zoom out a little bit again. Do you see now? So in this example, if we look at the first file or directory, the etc, then in yellow we see the user's permissions. That's always displayed first. So the user has read-write access, and the next one is the group, and as you can see, there is read and there is access, but there's only a dash in the place of the write. So this means read access but not write, and same for the other at the end here. And if we look at the next line, there is the same format, but this time there is read-write for the user and read for the other two. Then additionally, we have this line lonely D right here. And that only means that this is a directory. And often you will be able to identify that because there's either a 0 on the size or the same number for every directory. Plus you can see this slash at the end in some implementations and configurations of the ls command. Okay, enough about targets. Now we're coming to the last part of this episode. Change mode. Change mode is the command for altering permissions on a Unix and Linux system. And you do change mode and then something and then the file name like test.txt. But what do you type in the middle right here? Well, let's say we want to give those permissions for the files that we see right here. So read write for the owner and read for the other two. Then we have a couple of options. We may construct a string which looks like this. U equals read write group other equals read. So if you put this string in the middle here, then you will get those permissions. That's one way. Another way is to give all the read permission, and then the user will add the write permission. So this is a plus, U plus W. So there is a lot of possible ways to define those groups. If you leave out the A and the U, etc., and just do plus read write, then it applies to all three groups. And you can also do A equals nothing to remove all the permissions. I do that sometimes. So I run this command and then I specify like group plus R or something like this. Okay, that is one way, which is good to use when you are setting permissions that is not very common. But if you are changing similar permissions like often, there is an easier way, and that is using numbers. So now we come to this 755 stuff. What does 755 mean? Well, the first number is the user, this is the group, and this is other. And if we go back to the first slide right here, if we combine the 4 and the 2 and the 1, then we get a 7, which means that 7 is read write access. And the 5, well, there's only one way to construct a 5, and that is 1 and 4, of course. So read and access, that is 5. So this command means that the user will have read write, group other will have, no, the user will have read write access, and the group and other will have read and access. That's correct. So 755 is something you use a lot because you want to give access to directories and run permissions for scripts and programs. And another one which is very common is the 644. That means user, read write, group other, read. That is usually what a regular file will have by default. The directories most commonly have the 755 by default. And finally, another number which I use often on home directories is 700, which means I am the only one with any permissions to even access my home directory. What have we learned today? You have learned about Linux file system security, that there are 3 parts to it: the file permissions, the targets, and the change mode command. Let me say a couple of words about the change own, by the way. As you might have guessed, the change own command changes the owner of a specific file. So let's say there is a user called user5, and you want to give them the ownership of a directory. Then you do change own user5 and then the directory like etc or whatever. If you want to give a specific group as well, then you add a colon and then you type the name of the group. So if you have a group called users, you will type user5 : users. Today you have also learned about the read, write and access permissions and their flag and the numeric and binary representation, and how you can make use of all of these, combine them in infinite ways. You have learned how to use the ls command to check the permissions and what these different characters mean. You have also learned about the 3 targets: the user, the group, and the other, which you are able to set permissions for any file or directory in the system. And finally, you have learned the change mod and the change own commands, which changes the file and directory permissions and the owner respectively. Okay guys, this was a new format using my iPad to draw those things. I think this is a good format for these kind of videos. Let me know what you think in the comments. And more C videos are coming up, so please subscribe by clicking the little red button on the bottom right on your screen if you want to subscribe. And thanks for watching, and thanks for today. Okay, so how will our file encryptor work? Well, we're gonna create an out file which consists of the first 2 bytes is a random number between 1 and 65,536. Then we will have some padding. So if we have the random number 500, then 500 bytes of random bytes will follow. Then we have a 256-bit hash value, which will be our hashed password or hashed encryption key. That's so we have an ability to check if we have supplied the correct password or not. And then after that, all the contents of the file. And all of this will also be encrypted using the same key as is hidden in the SHA hash. And if you want to know how this works and why I need to do all of this, and I have recorded a special episode just for that, which I will also link to in the description. Okay, so let's start coding. As usual, I'm gonna start by defining the main, so I know what functions I need and when to do them, etc. And then I will start filling out those empty shells with real functions. I call it a function signature driven software design. Okay, so let's include stdio and all the other ones that let's put that in the H, by the way. So we'll simply include fse.h, and inside of here I will put all my regular include files. Perhaps we won't be needing all of them, and then we can remove them later on. But this way we don't need to pause all the time by looking at and finding these include files. String.h, and finally we also need our very own arc4.h. And let's create a signature for our main int and char double star, like so. So how do we want to structure this? Well, we're obviously gonna need an arc4 instance and we are gonna need a key, an in file, and an out file. So char, or let's use our own integers. So int 8, let's make it easy. We can convert to our own when we need it. So char, and what did I need? In file and out file, and we're also gonna need an in fd and an out fd. So that's a file descriptor that we get from the open syscall. And we're gonna need an int 8 for our key. And then we need a couple of sizes. At least we need the size of the key. So let's do an int 16 key size, like that. Okay, so if argc is less than, how many do we need? 1, 2 is less than 3. Then we're gonna print to standard error and tell that the usage of our binary file is in file out file. And the first is argv, and that's all. There we go. I hope the text size isn't too small for you. And then we're simply going to return -1. And now that we have enough arguments, we can assign our in file to argv1 and our out file to argv2. A little bit easier to handle, so we don't have to remember which these are. Next step is asking for the key. Well, let's open the file in file first, because we want to abort early if we're not able to do that. So in fd equals open, and we're going to supply the in file, and we're going to do read only, like this. And if in file is less than 1, printf std unable to open. No, let's not. Let's just do print error open and return -1. Okay, so now the in file is open. Let's do the same with the out file, by the way. So out fd equals open, because the file may already exist with the wrong permissions or be badly formatted, etc. So let's open both. Out file, and this is write only, and we also need create. So we create the file if it's not there already, and we also need permissions for the file, and that'll be 00600. So only our user will be able to read and write that file. And if this open operation fails, then fd will be the less than 1, and in that case we want to close our in fd, and then we'll do the same as before. this. Okay, so now both our files are open. Let's read the key. So key, let's see. We need to have a function which reads both the key and the size of the key, right? But since we are reading the input from the keyboard, we can just do a string length on it. We need to improve this when we do our much more secure version in the future sometime. Okay, so key equals read key, and maybe we'll supply some kind of a prompt. Key, like so. And in this case, I will do an assert. So we also need to include all the assert stuff. And that is basically two things we need to include. Assert.age, and we need to define GNU source. If we don't define the GNU source, the assert function will still work, but another function, which is assert p-error, will not. But if we have that definition at the top of our H file, everything will work perfectly fine. Okay, let's see. Int 16, no, it should be an int 8 pointer, which we called read key, and int 8 here as well. So we need to basically read the key from the keyboard and don't echo the characters to the screen. So let's see, we'll wait a little bit with that. We're gonna set our, what did we call the key? Key size. Key size will be equal to the int 16 of string length key. Now let's do char like so, and then we can change our key to int 8. Okay, so we have read the key. Next step is to start reading from the standard. No, the next thing is to start writing to the file. And the first thing is those 2 bytes of padding length, which will be completely random using a secure rand function. So we need that secure rand function. So let us let's create an int 8 Let's see. We need to have, let's do int 16 and we will call it the padding length, pad size. And the actual padding will be stored inside of that int 16, right? Yes. And we need an int 8 array for the actual padding bytes. Like so. So basically we will do something like pad size or pad size equals secure round, and we need 2 bytes, something like that. Pad size I'm not sure if that's the best way though. It's a little tricky to store these kinds of data. Well, how do we store it? Because we're gonna need it for an int 16 like this, but also for a long string of characters. I think we'll do 2 different variables. That must be the easiest way. So let's say we have an int 16 called pad size 16, and we also have an int 8, which is the pad size 8. That should be it. So pad size 8 will be equal to this, and pad size 16 will be equal to let's see, we need pad size 8 dereferenced. So let's have it's a lot of variables for the same thing. This can probably be done much better, but I don't care right now. I just need something that works. So pad size 16 equals the int 16 version of pad size 8. And the actual pad size will be pad size 16 dereferenced. That should be it, right? I think we need to print this out to see if it really works. Pad size %d, and this will be the int of pad size. This is a lot of different conversions. Well, let's see if that works. Right. Okay, so the only thing is we have the opening of files. This is commented out, and then we have this. So then we can start with this secure RAN thing. Yeah, let's do that. Close infd, close alt fd, free pad size 8, return 0, like so. Okay, so how do we create a cryptographically secure function for generating random numbers? There is actually a system call which is called, if we go into the urandom, I think there should be, get random. And that is a system call. So basically it returns the size of a buffer of a specific size. So if we say that we need 8 bytes of random data, we get that, perhaps, or we get less. That depends on the entropy pool. So basically this function uses a lot of different signals, like what has occurred since the computer booted up, all of different things. It puts in a big pool, which is called the entropy pool. So you can only create a finite amount of these random bytes between all the whole system. And when you run out of entropy, you just have to wait. So you can call this function with 2 different flags. First, we're going to call it with give us all that you have, and exit if you don't have enough. And if we don't get all the bytes, then we will call it again, but we will put a message to the user that this may take longer than usual. And then we'll call it with the other flag. Well, the alternative is that we don't use a cryptographically secure version of this, and I want it to be unhackable. So this is the stuff. We're gonna use this random, which means that it doesn't use a pseudo-random function, which is not good enough for cryptography. So we need to supply the random, and then it relies on the entropy pool. And basically we will let it be non-block the first time around, and the second time without the non-block. Easy as pie. So size, return value, and we have the buff and the size. And I think we can supply a null buffer to get it on the heap. Or perhaps not. Never mind, let's allocate that ourselves. And where is this? sysrandom.h. So let's go into our h file and include sysrandom.h. And let's see, this will return an int8 array, and we called it secure round, and we just need to send number of bytes. Let's do int16. And let's create this function. So int8 array and secure round. We will have an int16 size. And we need to have an int8 pointer. Let's start by checking the size length. So we need to assert that size is bigger than 0, and yeah, that's basically it. P will be equal to an int8 malloc of size bytes. We will assert P, or by the way, let's not assert P. If yeah, let's assert P. If we run out of memory, so malloc will start to fail, everything will fail anyway. So okay, so now we have our buffer. We need something that catches the return value. Size t and will be equal to get random, and it will be P. Perhaps we need to, no, we probably don't need to typecast that. And then the number of bytes, that size. Maybe we need to typecast this to a size t. And we need the flags. Right. So this and then we have the same but non-block. So we need it to be random, and we need to be non-block. So this may return, let's do if n equals size, then everything is okay, and we can return p. And if n is less than 0, something has gone wrong, and we need to return 0. Else, it means that we did not get enough bytes, which means we will have to run this again. So we do f printf stdr warning entropy pool is empty. This may take longer than usual. Something like that. And then we call it again, n equals get random. And this time we need to increase the pointer p plus equals n. So we will supply p, and this time this value will be size minus the n bytes that we have already gotten, right? And we need to supply the grnd random, but not non-block. There we go. And if n equals size, we return, we need to deallocate, by the way. And right. Yeah. Then we need to save a copy. We can't free it if we have jumped it around. Well, we can just jump it back. That's better, actually. No, we don't know how many bytes. Okay, let's do it this way. No hesitation. So, if n equals size, then we return start. If n is less than 0, then we will free start and return 0. And in all other cases, it has failed again. So we can simply do else here instead. And this should be our function. So if we call it with 2 bytes, like this, and everything is okay, we should get different result each time. Let's see if this even compiles. Nope. But when does it ever first time? Int main. Second argument of main should be char star star. What did I do? I forgot 1 star. We can't make the main a single star. There we go. 1 gone, a couple more to go, right? Open. Did you mean p open? No, I did not mean p open. That's a library called for noobs. Let's see. Open, what do we need? man2 open, what do we need? Okay. So let's include this FC and TL whatever. If in file is less than 1, comparison between pointer and integer in file. Where is it? If in file, if in FD, alt FD, this one was right. In date padding, unused variable. Key size set but not used. Warning, unused variable. But it compiled. So let's see what happens. FSE. Yeah, we need to mock these files. Let's just touch in file. And let's do FSE in file, out file. 45938, 40950. Yeah, this works perfectly well. Great. Okay guys, let's create the read key function, which will be a quite simple function. It's going to read the key from the keyboard, and the only thing we have to make sure is that we don't echo the characters to the screen. So the only thing we're gonna have right here is a prompt, and what do we need? We need a buffer represented by a pointer. So let's see, we're gonna return an int 8, so let's make this an int 8 pointer. And we're gonna, let's see, we need a temporary buffer on the stack because we don't really know how many characters to allocate. So let's say, let's do unsigned char. No. Let's do char, and let's say we have a max limit of 2048 bytes. Or that's a bit much perhaps, because the biggest size in a 2048-bit encryption system is 256. Okay. So let's make it 255. No, 256. Because as you know, this isn't the index. This is a number of chars that we want to allocate. So counting the 0, it's 256. Okay, so let's begin by writing the naive version of it that echoes to the screen. And then we will simply fix that afterwards. So how do we do with this? We don't have to make it so difficult. Let's just begin mem setting. I shouldn't call this argv buff. We're gonna mem set the buffer with 0, 256 of those. Then we are going to read from standard in, standard out, standard out. From standard input into our buffer, and we have to, no, we don't have to cast that. And we're going to read a maximum of 255. So we have room for the ending 0 as well. Okay, so now we have read one line. We need to remove the ending new line from the input as well. And we're gonna need an int for our, let's do an int 32 for our length. Or no, why should we just be as big as that? An int 8 should cut it, right? So size, and we'll simply just call string length on the input. Buff, and then we will, let's see, if we have A, B, C, D, that's the length of 4, and the indices will be 0, 1, 2, 3. And if we have a new line at the end, this will be index 4, and the size will be 5. So let's do an index as well. and index will be the size -1. So let's do let's point our pointer towards buff plus index, and let's zero that out like so, and then we will allocate our buffer. So this will be an int malloc size, and if malloc fails, everything will fail. And if it works, we will simply copy our string to p from buff, and the size will be size, right? Or maybe -1, by the way, just to make room for everything. Okay, let's remove this. And did I forget anything? Yes, we need to typecast a little bit. So the size is an int 8. So we need to make this an int 8. No, wait. An int 8 like this. And we need to send we can send the buffer as is. Read buff, memset buff. Int 8 malloc. I'm gonna string copy to p from buff. I think this will work, right? Perhaps we need to cast this one. And then we'll simply return p. We also want to print our prompt. Let's not forget about that. So let's do printf, and then our prompt and the space, and we'll give the prompt right here, and then we need to flush the buffer because we are not ending the printf line with a new line, so we need to flush it manually. Standard out like so, and here is our first version of that code. Did we create our yes, but we didn't make this an int 8. This should be a char. Okay, so let's try it out without the echo, with the echo. Where are we? Key equals read key, third key. Yeah, let's try it. So make Okay, what is it? Differ in signedness. P equals buff plus index. So it's this line. So P equals buff, which is a char. So we need to do int a star plus index. Don't think that will be a problem. And P equals, let's try it out. Okay, we got a binary. Yeah. Okay, so let's try it out. In file, out file, key ABCD. We still have that pad size thing. We can remove that, but it seems to work. Okay, guys, let's end there for today, and we will continue this project another day. Don't forget to like and subscribe, and thanks for watching, and thanks for today. Let's remove that. So printf pad size. Yeah, let's just delete that. Okay. Okay, guys. So now that we have our key retrieval function, we will need to improve it a little bit and remove the echo of the keyboard characters from the screen. So in order to do that, we need to use a function and that is located in a header file which is called termios dot h, and let me see if there are any examples. Let's see. Okay, so there doesn't seem to be any examples, but what we need to do is first, because they're in a terminal, there are a couple of options that defines how the terminal should work. So we need to do two function calls. We need to retrieve the current options of your terminal. Then we need to alter one of the flags to remove the echo. And then we will do another call to change the flags. So that's how we toggle the echo. And then we will just call our own function twice. Once for removing the echo and once for getting the echo back. So let's see. Let's begin by importing that H file. It is called termios.h. We also need to create a function, let it be a void function that we can call toggle echo, and we don't really need any parameters, like so. So if the echo is enabled, we remove it, and if it is disabled, we put it back. Perhaps we should, yeah, this will be easier. Let's do a change echo instead, and then we'll take a bool, which will say if the echo should be enabled or disabled. So we need to include the std bool.h as well, like so. So let's write the function, and it will be a void function that we'll call change echo, and we'll have a bool enabled, like this. Okay, so the next step is we need to create a structure, an instance of a structure for this kind of stuff. And let me see which one it is. We're going to use these two functions, which means we need a struct terminals. So let's see. And I closed the window. Let's go into our directory. It is called FSE, right? No, it's inside temp FSE. There we go. Okay, so first I need to reset the home directory. Like that. And we need a struct terminals t, and let's allocate some memory for it. T equals struct terminals malloc, size of struct terminals, like so. Let's copy both of these function signatures to make it a little bit easier to use them. So first we call this get attribute. So tc get attribute, and the fd follows the same logic as standard in, standard out, standard error. So this should be 0. Get attribute, and then we have the t, and that's basically it. Perhaps we need to send a reference to the T. Let's see if it works or not. And let's see what flag we need to alter. I think it's called echo. There's a couple of them. I think we just do the echo. Okay, so we need to do a binary operation. So basically T is equal to, no, T dereferenced is equal to, let's see, we need to remove a flag, so we will do a logical AND operation. And that might seem a little bit non-intuitive, but basically if we have X and Y and we let one of them be 0, then this will be 0 as well. If we use the OR, it would still be 1. So we remove echo, and now we need to do an if first. So if enabled, then we're gonna add the flag. If it is enabled, we're gonna remove it like we did. And if it is disabled, we want to enable it. Or what is most intuitive? Perhaps we should treat this enabled as if it should be enabled or not. So if it should be enabled, then we should do the OR operation and remove the echo. Else we do the AND operation. And then we basically do the other one, tc set attribute, and we give the file descriptor int optional actions. I think we can do the 0 there. And then we need to give the structure. Let's see, construct terminals, yeah. And that's it. So let's see if this works. In our, not this one, in our read key, we will send the prompt, then we're gonna do change echo, and we want to remove the echo. And then we will do it again, change echo, and this time we want it to be enabled. So true, it should be false up there, right? Okay, let's see what happens. Make, okay. Invalid operands to binary or, yes, of course. We don't do it on the whole structure. We need to do it on one of the fields inside that structure. So let's see which it is. Input modes, output modes, control modes. So should either be could actually be any one of these. Let's see, if we search for echo and we go upwards to the headline, C flag constants. Okay, so the same flags are for all of these. Or what did it say? C flag. Okay, let's try it on the C flag. It's tough to remember all of these different functions that you only use once every couple of years. Let's see, where were we? Here. So this looks right, but we're gonna do T C flag and T C flag, like so. Not TC flag, it should be C flag only. So, right, C flag. It's a pointer. We need the arrow, not the dot. Let's try it again. TC undeclared. TC flag. Okay, now what? Invalid type argument of unary star have TC flag F, aka unsigned int. Well, we should probably not dereference that one. Where are we? Let's do it like this. Okay, so now we only have one error left. Has no member named C flag. It's tough to get this right, huh? It should be C flag. C flag, right? Let's double check this time. C I flag. CC flag. Let's copy this instead. So remove the whole thing, paste this in, remove the whole thing, paste this in. This time I'm feeling lucky. Okay, let's try it out. We have infile, we have outfile. Okay, didn't really work. Why didn't it work? Perhaps it's because of this 0. Or maybe they want us to do this on the standard out. Because logically it could really be either one, right? So let me try it again. Nope. Let's do an S trace. It runs the command. So let's see the first time. Where is the first time? Here we get the flags and it has the echo. Then we set the flags. And do we have the echo? No. Well, yes, it's still there. Why is that? Let's see. So, oh, I forgot to free that one as well. But that's not the cause of the error. Let's see. So we get the flags if enabled, and it should be false the first time. Read key, change echo false, yes. So TC, oh, I mixed them, didn't I? If it should be enabled, we OR. If it should be disabled, we AND. Okay, so let's put this way instead. And let's go back to the 0. Let's try it again. In file, out file. No. Let's try it on standard out then. So 1, 1. Perhaps we shouldn't do it on the C flag. The other one, what did it say? One has to do with input and one has to do with output. Input modes, output modes. Is this an input mode or an output mode? An echo? Well, it's both. Well, let's try it with an I input mode on the standard input. So I flag and I flag. If it should be enabled, we no, we had this right the first time, and we want to do it on the standard input and the standard input. Okay, something happened. I can't press enter anymore. That's pretty weird. So we did change it somehow, but not really the way I intended. So let's just try one thing. If we do one here and we do it on the I flag, same thing. So let's do the I flag on the 0. No. Okay, so get attributes, file now, standard input. Okay, so now I looked it up. We should do it on the standard input as we thought, but we should do it on the L flag. So let's try it again. In file, out file. Okay, that's a bit weird. No, that's not right either. Okay guys, let's end there for today, and we will continue this project another day. Don't forget to like and subscribe, and thanks for watching, and thanks for today. What's up guys, welcome to today's show. Today we are gonna code a safe string library. And what is a safe string library, and why is it needed? Well, let me show you an example. So let's say we have a main, and I'm not going to do any error checking now, so I will simply take the arguments. If this were production code, I would of course do a check so we don't access parameters in command line argument that's not there. Let's create a string. Let's call it str and let it be 8 in size. And then we will create, let's do just a char pointer, and I will let it be equal to hello, like this, and I will include 2 files, standard IO and the string library, like so. Okay, so I want to put this p string into the str variable. So then I use string copy, and the target is str, and the source is p. So this will copy the contents of p, i.e. this hello, and put it into our str. And then I will simply print f this str like so, and return 0. Okay, let's compile this. And we run it. No problem there, right? Let's, sorry, I'm gonna use nano today so you get syntax highlighting. Okay, so let's instead, well, let me do like this. If argc is less than 2, return -1. Just a simple check. And we're going to take one argument from the standard input. So instead of doing p equals hello, I'm going to do p equals argv1. So we take the first command line argument. We compile again. And if we run it without any arguments, nothing happens. What if we were to do the hello string again? Then it shows. But what if we were to do something bigger than 8? Like this. Segmentation fault. The program crashes. Why does this happen? Well, these variables are placed on a stack. If we only have room for 8 characters in this variable. So if we copy a lot of those with this string copy, it will start to overflow the stack. So basically it may overwrite variables, In this case, though, the str is on the top of the stack, so it will start overwriting other things like return addresses and saved stack pointers and other important stuff, which basically means that the program will not know how to return from this function, and it will jump into some memory address which is not right, and it will crash. So when you're dealing with strings, a lot of the work is to make sure this doesn't happen. One possible solution to this is that instead of using the string copy like this, you add an n in the middle, so it's string n copy. Because then you can add a third argument, which is the biggest number of characters to copy. So if I put 7 in here, it can never copy more than 7 characters. So let's try this again. Hello, it still works. And if we do this, now it will only do the first couple of characters and then exit without an arrow. So if it's this easy to fix this problem, why bother with it? Why make a video about safe string library? Well, this is only one example. A lot of the times you don't use functions like this. You edit the strings yourself. Or what if you need to read all the lines in a file, for example, and put it inside of a string variable? How would you do that? You need to allocate and reallocate memory so you have the correct amount of memory all the time. So it's not that straightforward to create a safe library for this. Okay? So my plan is to make something that will work like this. So let's remove stuff in here. So I want to do something like this. I want to create a string. So this is my own variable, str, and I will initialize str with some initialization function, like let's call it init, and and it will take what will it take? It will take a string to begin with. So the first string to put inside of this str variable, let's say hello, like so, and I will not use any numbers, so nothing like this, that we only need 5 characters, etc. I want to make this library as easy to use as possible. And what if we wanted to add like hello, the word there, so it's hello there? Then we can use a concatenation function. So we just provide the string a variable name, and then what we want to add to that string. So let's say there. And then it will automatically take care of allocating the memory necessary in order to add this to the string. And if we want to print this string to the screen, we can do this by just referencing, let's say, well, let's call it fold, and then we just give str, and it will print the contents to the screen. And then we only need some kind of uninitialization function. So let's say uninit str. So we can easily use this concat inside of a loop and read an entire file. It can be a very big file, gigabytes or even larger, and it will put it inside of this string construction. That is the plan, anyhow. Let's see if we manage to do this. I'm going to clean up a little bit here and create a simple makefile. So what do we need? We're gonna have a file called safestr.o, which depends on safestr.c, and we want to compile it using let's see, $roof or caret, or I'm not sure how to pronounce it. This means the source, the C file in this case, and this means the target, the .o. And we're going to do -c, and yeah, let's not overcomplicate stuff. That's good. And then we will have the safe string SO, which depends on safe string .o, and then we will run cc and the source -o, and this will be the target. And now we need a couple of options, and I don't have them in my head right now, so I will use a variable which I call options, which I will put some content into later on. And when we do all, I want to first clean and then make a safe str.so. And finally I will put in the clean, which will remove all the .o files and the .so files. So something like this. So if I just do touch and let's see, safe str.c, I should be able to do make, and it creates the .file. We do get an error here, but that's only because we have empty files. This for make clean, and it's gone. We also need a safe str.h, and I'm gonna create a new window. I'm gonna go into code and safe string. I'm gonna set my home directory to this directory, and in here I'm gonna open the .h file and .env safe str.h, safe str.h, and in here I'm just gonna open the C file. So safe str.c, safe str.c, and we're gonna include our safe str.h like so. And as usual, I will begin by defining my main. So we'll see what I want this to do. So let's create a string which we'll call str. We're going to initialize it like before using an init function which we hasn't made yet, and we will put in hello, and then we want to concatenate the str with the word there, and yeah, let's do something like that to begin with anyway. And then we want to uninit str, and in between we want to print it. So printf %s and fold str. Return 0. Okay, so this is basically what we want to achieve. Okay. The first thing I'm going to do is include a couple of libraries, just the standard ones. So uni std.h and stdlib.h, include stdbool.h. This is quite new, by the way. You might have to install the latest part of GCC if you want this. So this adds native support for booleans. stdbool.h And I usually include string.h, but I'm gonna wait a little bit. My hope is that I don't need that and I can write my own functions for that instead. However, I do need assert because I don't want to worry too much with error handling when I'm doing a video. And I also need to do a definition for GNU source, and that is so I get the function assert p error. So basically this function is inside of this file, but it won't be defined unless you define this one. And it's basically a combination of the assert function and the p error, the print error function, which is quite nice, I think. But then you also need to include the r number.h, like so. Okay, so let's define our structure. Our string structure. So I'll call it S string. And what do we need inside of this? Well, we need some kind of a counter so we know how many bytes of contents we have in our structure. So let's make this an unsigned int, and we can call it count. And we do also need the buffer, the actual string, and this can be done a couple of different ways. I could define it as a char pointer like this, and then I allocate memory to this one. But an even cooler way, I think, is to use a new function in later C versions that you can create a char array, basically a string, like what we're gonna call it, data. And usually you do something like this, so you put like 64, so it will have 64 bytes in it. But if you put a 0 in there, then you define the variable but you don't create any space for it, which means that you can only do this at the end of the structure. So this entire structure will be variable length, and we can just increase and decrease the entire structure when we need to handle the strings, which is kind of nifty, I think. Okay, and I will type def this struct s string to string with capital S. I will also create a couple of function definitions. We have a main with an, I'm not sure if I'm gonna take any arguments, but let's put them here to begin with anyway. And what else did we say? We want an init function. and that init function will take a string, an initial string, and we want to return a pointer to a string, so our own structure, like so. And then we want a concatenate function, which will take a string pointer and another string. And this will return a bool if it was successful or not. And we also need an uninitialization function, but for the time being I think I'm gonna do a macro. Perhaps I need more intricate functionality later on, so I'll change that, but for now I will just do this. Uninit x will be free x, like so. So let's start by creating our init function. So it will return a string pointer, and it's called init, and it takes a initial string, like so. And we need a size variable, unsigned int size, and size will be equal to length of str. So we do also need to define that length function, and that will basically be let's see, that will basically be, well, it will be pretty much the same as the regular strlen, right? So unsigned int length, and it takes a char array. We need an n and a pointer. Let's do the const right here, and we'll create a pointer for n is equal to 0 and p is equal to str. We're gonna loop as long as, let's see, as long as the thing that p points to is not 0. And in each iteration we're gonna increase p, and we're gonna increase n. And we don't need anything else, no body of this one, so I'll add a semicolon at the end, and then I'll just return n. And I want to create a function declaration for that as well. So unsigned int length, and it'll take a char star, like so. Okay, so now we have the length of the string. And since this is the initialization function, this will be the first string, so we don't have to think too much about it. I do have, however, one additional byte allocated, and let's allocate no. So it will be, this is how much we need for our string, but then we also need the size of our structure, which will be struct, what do I name it, S something, S string. Okay, that should be enough memory, right? So let's create a string P will be equal to string malloc size, like so. And we do also need to zero this structure. So one new way of doing that, first we need to assert that P is not 0. Then we're gonna do a, let's see, P, I think it's something like this. P equals this. I think you do it like that. Maybe we need to dereference. Let's see if that works. Okay, so we have the empty structure. Now we want to copy the actual string into there. So mem copy and into P data. We want to copy the string and let's see, we need a variable for the length. So let's do an n as well. So n and size, and we let n be equal to the length of the string, and we substitute this by n, which means we can copy n into the string. And then we'll just return P. Okay? So let's comment these out because we're not done with them. And not this one either. But the initialization should be okay, and let's do a printf so we see that it's working. So %s, and this will be str data, like so. Okay, let's see what happens. Oh, assignment discards const qualifier. Okay. So let's do length. I think it should be okay to add the const right here. Did I have the const here? No, I didn't. And init, we need a const there as well. So const basically means that we cannot write to that argument. Same here. Okay. So const, and maybe we don't need it there. Init const. Okay. Assignment discards const qualifier p equals str. Okay. We have a typo in the header file. Let's see. Main. That should be just int. And what did we do wrong here? Let's see. It's in the length function, I think. N equals 0, p equals str, p plus plus, n plus plus, return n. Let's see what it's. Let's see what it said. Okay, it didn't like this construct. Perhaps I need to add some options so it uses the new standard. Let's see. If we add dash std equals let me see, c2x, and let's add it here as well. Std equals c2x. Still doesn't like it. Perhaps it needs the space there. Expected expression plus P equal. What if we do the slightly older standard and put a 0 in there? No, still does not like that. I think I need to typecast. That's probably it. So let's make it so, and then I do string like so. Okay, now it works. Mem copy, okay, what do we need for that? Mem cp, okay, it's side of the string dot age. Let's create our own. No, safe string. Let's see. So we have a void pointer and let's do bool instead. And we can name it copy. It's gonna take a void pointer to a destination. It's gonna take a const void source and a const unsigned int n. And this function will basically be like this, but not exactly. But let's start there anyway. So const char p let's do like this. So const char p p source and just char, no, not char, void. And right here we just do void p destination. And we do a for where unsigned int x. And inside here we set x equal to n. We set p source equal to source. P destination equal to destination. And we're gonna iterate until x is 0. And each iteration we will increase p source, p source, and p destination. And what are we going to do? We're going to take whatever P destination points to and set it to what P source points to. We can make this a void because not much can go wrong, and if anything goes wrong, then the program will crash. So like so. Save, and we need a function declaration. So void copy, and we have a void pointer for the destination. We have a const void pointer for the source, and we have a const unsigned int, like so. Also, we need to change so we use our own function. Where is our mem copy? Right here. So let's just do copy. Okay, it's getting better. Dereferencing, okay, it doesn't like dereferencing void. That's right. Okay, so let's go into that file again, and let's change those pointers to char instead. And let's typecast a little bit. So P C is equal to the char version source, or the const char version, and this will be equal to the char version of pdest. No. Like so. Okay, int main, conflicting types, that's right. We need to add our arguments. Int argc char argv, like so. And it compiles. It does, however, compile into a library, which is a little bit difficult to debug or to try out. So let's alter our make file a little bit, and let's change this. And this. I don't think we need to change anything else, actually. Okay, let's see what happens. Segmentation fault. Okay. Yes, trace F. Didn't say much. And ltrace didn't say anything. Let's double check the code. Let's see. Save string.c str data. So n equals length of the string. I think we need to try out our two utility functions so we know that they work. So we have our length and we have our memcopy. Let's start with the length. We'll check the length of A, B, C, D, E. That should be 5, right? Okay, no problem with that one. So how do we check our memcopy in an easy enough way? Let's create 2 char buffers. So buff1 16 and buff2 16, and I'm gonna string copy into buff1 low new. And I'm gonna mem copy into buff2 from buff1 and let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I'm gonna print the contents of buff2. I'm also gonna memset both of them to zero them out. Like that, and I need to temporarily add the string library. Memset. Oh, yeah. Wrong punctuation. Memset. There we go. Hello you. Okay, so both of these functions seem to work. So how come my stuff doesn't? So str equals init and printf str data. Perhaps it's about null termination. Yeah, that's probably it. So where's the init function? How much am I allocating? N plus 1 plus size of this. So there's room for the null terminator. Let's see. If I create a regular char pointer, char pointer, and char pointer should be equal to p data plus n, and that should be a 0. It should work, I think. Still segfault. Init hello. And take this string. N equals length string. Size equals n plus 1 plus the size of this. P equals string malloc size assert P equals string 0, copy to P data, the string, and what happens if I remove this line? Okay, so that's where it segfaults down. Even though the copy function actually works. So p data string n, and n is the length of the string. Okay. I forgot to... I set the x to n, and my idea was to decrease it, and when it reaches 0, we're done. But I only did half of that thought. So we should add x minus minus here as well. Alrighty then. Then we probably don't need this stuff, since everything already should be zeroed out. There we go. Yeah, now it works as intended. Good. Sometimes it's those small little things that makes you have to troubleshoot forever. Okay, where were we? Safestring.c. The only thing we have left actually is to create the concatenation function, right? Which basically merges one of my strings with a regular string. So let's do that. And that is a bool. And what did we call it? We called it concat. And it takes a string pointer as an argument, and a const char source. Okay, so first we need to calculate the memory consumption, and we do need an unsigned int n, which will be equal to the length of source. So the size, we can make it in 3 steps. Let's do a current size as well. So the current size is equal to the destination strings count plus 1 plus size of struct s string. So the size of the structure and the contents, that is the current size. And the new size should be equal to the current size plus n, the number of bytes we need to concatenate. So then we have the new size. We also need a pointer, string p, and let's see. No, do we really need that? Yes, I think we do. So P is equal to string, and this time we use realloc. And the old memory segment is the destination. Yeah, it's a destination. And the new memory requirements is the size. That will be our P. And if P fails, we'll simply return false. And if it doesn't fail, then we have the memory we need. So now we just need to copy the new string. So let's do it basically like we did before. I will create an, let's see, I will create a regular char pointer, and that char pointer should be equal to p data plus p count. So basically it should be equal to the old count. We need to increase by with that, so we come to the end of the old segment, and that's where we will put the new data. And then we will simply copy to p data, no, to cp. And what should we copy? We should copy the source. And how much of it? It should be n. Like so. And then we will simply do p count plus equals n. So we increase the count. And we return true. That should basically be it, right? So let's go down here. I will remove this temporary printf, and we'll add back our concat. And right, we need this fold as well. The fold should simply return the value. Let's do it quickly. Char fold, and it should take a string as an argument. And it should simply return string data. Easy peasy. Let's create the function definition as well. So char fold string star, and we do have our uninit as well. So maybe this compiles. Let's see. Okay, what does it say? It should be str, right? Where is it? Here, concat str. There. We should add the 0 byte at the end when we concat. So let's see. So CP should then be equal to P data plus the new P count. And let's 0 that one. Like so. It compiles. Hold your breath. Almost. It showed the there, but it didn't. It overwrote our old data. I think I know why. If we go to the init function, we don't really increase the initial length. So P count should be equal to n. That's right. N plus 1. Yeah. Okay, let's try this again. Hello there. Okay, so what have we learned today? We have learned how to successfully create a safe string library with a concatenation feature and some other stuff. And I will leave as an exercise to you to create an equal function that you can use in order to check if two strings are equal. And it should work with our string data type and regular strings in any combination. If you like this content, please like and subscribe. There will be a lot of more C videos, both beginner level and very advanced. I have a lot of interesting stuff in the pipeline. So thanks for watching and thanks for today. Okay guys, welcome back. Last week we began creating this Toralizer tool, which tunnels any Linux application through the Tor network. We wrote the first part of it, which is a SOX version 4 client. So this is what we have this far. We can supply the destination host and port. So let's take my web server as an example. So we run Toralizer, and let's do this IP with a port of 80. And we connect to the proxy. Maybe it's okay, there we go. Sometimes when you use the Tor network, it's quite slow, but more often than not, it's quite fast. But as you can see, we connected to the proxy. We successfully connected through the proxy to the destination, and we communicated with the web server on the other end. So the biggest part is done. What we need to do now is the following. We need to turn the client into a library. So instead of using it as an application, we want to have it as a library, and that is a shared library, to be specific, .so files. When we have done that, we're gonna turn main into our own connect, replace regular connect, and we're also gonna save a reference to the original connect so that we can use it ourselves, because our current tool is using connect. If we look right here, so we connect to the proxy server using that system call, and that's why we need to save a reference to it so we can use it ourselves. We also need to grab the IP and port from original connect. So we will take care of the arguments that the application sends to its connect, and we need to take the IP and port from there instead of reading it from the command line arguments like we do now, and then we can proceed by doing what we do now. And then we will just leave it to the original application to take care of the rest of the communication. So we do our thing, and then we exit our function and let the program take over. Okay, so how does this technique work? Well, when you compile your code, you have two options. You can compile it statically, so it's statically linked, and that means that if you use any library calls, or system calls too for that matter, like printf or anything, that code, the printf code, will be saved in your program's executable file. But that's not very optimized, because if every tool on the whole drive would be statically linked, then there will be a lot of duplications, because almost every application uses some form of library calls or system calls. So that's why we have the shared libraries. So instead of, and that's what's usually in use. So we have like a database with a lot of, with a printf code and with a scanf code and even wrappers for system calls like connect. And when an end application needs to use any of that code, it will collect it from the central repository on the disk. So that's how it works. The thing is, there is a kind of prioritization order, so which we can influence. So if there are two functions with the same name, which one that's gonna execute is decided by a list, basically, and a prioritization order. So if we name our own function connect, and we have compiled this as a shared library, then we can make any application use our code as priority one. And in that way we can intercept and hijack the library call and system call, because all system calls have wrappers in the libraries. Okay, this will probably be a little more clear when we have written the actual code, tested it. And this is not my own invention, this technique. I am following a website, let me just find it, C shared library function hook. Here it is, at R. Jordanes. So it's pretty simple actually. So put S is a function which basically works like printf, but not as advanced. It prints a single string on the screen. So that's the one that he uses in his example. So as you can see, he creates a function with the same name and same signature. He creates a function pointer also with the same signature, and that is for saving the original put s in this case. And then he gets the reference from this dlsym function. So basically you give the RTLD next and the name of the function, and it gives back the memory address where that function is originally located in memory. And then he just does like this. So he checks if you send the argument hello world, and in that case he hijacks the original put s call and changes the message. In other case, he just runs the original put s with the same arguments. So this is basically what we're going to do. We're not going to have a condition because we are always going to hijack the original one. We are, however, going to use the original connect function to make our connection to the proxy server. And then we compile it as a shared library. So there's a couple of additional switches we use. And then we get a .so file. And then we basically tell the system to use our library instead by this ld preload environment variable. So we're going to create a small bash script, in our case 3 lines big, and that's what we're going to name Toralize. And then we're going to use that to set the environment variable and run the command. And yeah, that should basically be it. So let's begin. Let's start by grabbing the signature. So we do man to connect and just copy this exactly as it is, and then we go up to our main and we just paste it right here. Like so, and sockfd address len t, and we remove this, and so we basically turn our main function into this connect function. Like so, and we create a function pointer. And if you have watched my episode about function pointers, you know that that is done like this. I will paste the signature for this original function once again, and instead of connect I will just name this P for pointer. I'll put it inside parentheses and add the star, and then we remove this part, so it should be basically like a signature function declaration. And we use this to point to this DL sims function. And let me just see where it's located. So man3 DL sims, and if we don't find it in page 3, we do page 2. DL sim, perhaps it's without the S. Yeah. Okay, so it's inside of this dlfcn.h. So let's add that to our list of includes, and let's see if he included anything else, only the string. So, and I need to grab the first argument, rtld_next. And you might ask why I don't copy paste, and I try to avoid that when possible, because if I type this a couple of times I will probably remember it. rtld next, and the name of the function is connect, like this. and we initialize the socket, but we don't really, or let's do it like this, by the way. The curl application, or whichever we use, have already initialized their socket, but I think it will be easier just to pipe those two sockets together. Okay, so let me update the signature here as well, so I don't forget that, by the way. Because we don't have any main anymore. We just have int connect. It's int, right? Yes. Did I do int here? Yes. Okay, so int connect, int construct sock address star, socklen t. So we don't have a main anymore, because that's only for applications, and this is not an application. This is just a couple of functions which are free. Okay, so the application runs connect, and we don't need any of this. And we save this, we initialize our socket, and here we make the connection to the proxy server. Nothing will change about that, but we're not gonna call connect, because we would be calling ourselves. We will be calling this p, the function pointer, like so, connected to proxy. And we also need to change our request function. Instead of sending host and port like we did before, let me remove that. So we have int s, and we don't have this host. Instead, we need to grab the IP and the port from the arguments. So this is what the application provides. We have the socket file descriptor, we have the length of this structure, and we have the actual structure. So I think the easiest way would be to, I don't want to name this address. Let's call it soc2 and s2 instead. So s and soc, that's ours, and s2 and soc2 are the provided by the application. So we need to look inside of this and get the data that we need. So let's pass the whole structure of that instead as host and port. So we'll just do soc2 right here, and we need to change the signature for our request function, and that is of type struct soc address in and star. Struct soc address in star. And I think we need to do a typecast and send the reference. So where were we? Right here. So struct soc address. Struct soc address in I think we need to do it like this. If we get a warning or error, we will change it, but it should be alright. Struct sock address in sock2. So we send that whole structure to this function. And we need to change this as well. So that will be struct sock address in, let's call it sock. No, let's call it sock2, so we know what's what. Okay, so the destination port, we don't need to do HTON-S and INET address because it's already in the network byte order. So the only thing we need to do is reference sock2 SYN port. And for the destination IP, sock2 SYN address source address, like so. Perhaps we need to do some typecasting, but I don't think so in this case. Okay, so now we have the correct packet, and then we save that, then we send that packet. Enable to traverse the proxy. We can keep this for now. Successfully connected through, and this we will not have though. So as soon as we are connected, we are basically done. We don't want to close the socket. We do, however, want to pipe our socket with the end applications socket. So what does it mean, piping? Well, we need to do so everything that's being sent to S will also be sent to S2, and everything that's being sent to S2 is being sent to S, and same with the receives. So we basically become the man in the middle. And there is a good system call which is called dupe2, which does exactly that. So it creates a new file descriptor, and it will be the same value as the second argument, which means that this will be pretty seamless if we give S2. So dupe to S2, and then we return. Did we forget anything? I think we did most of it. Let's copy the compilation flags from this one. So we'll go into our make file, and it will be toralizer.so fpic shared lel. Okay, and I will begin by removing the Toralize binary executable because that won't be necessary. Okay, let's see what it says if we try to compile this one. Okay, DLSIMs, it should be DLSIM. Right here. And I enter down a little bit, and run make again, and host undeclared. Okay, that's the message. I don't think we actually need that one. Where is it? Unable to traverse the proxy. Successfully connected through the proxy. Let's just say through the proxy. Enter. Otherwise, we need to convert between network byte order and stuff like that. Perhaps we can change this later on instead, if we want to. Okay, it compiled. So, how are we going to test this? We haven't really created our bash script. We can do that now, by the way. Let's begin by checking what directory we're in and the name of this. So I'll just do a copy paste of this directory, and I will add this SO file to it. So this is the whole path to our library. And I will log in as the root user. I will go to user bin, and I will open up Toralizer, and this will be a bash file. So we need to have this interpreter at the top, or the hashbang. Okay, so let's export LD preload to this one, and then we want to run the commands, because we're going to run this as Toralizer and then curl or whatever. So we need to send everything that's on the right of this Toralizer. And there is a way to access all the arguments at the same time, and I think it is done like this. Okay, so first we export the LD preload and point it towards our shared library. Then we do the $, and I think it's the @, which will run all the arguments to this script. And finally we unset the LD preload like this. It's probably not necessary to unset it because it's the end of the script, but I think it looks a little better. Alright, so we save this and give it running permissions. Toralizer, and then we test it out and hope that it works. So network technology.org. We will try to do Toralize, curl, and an HTTP request against this IP address. Connected to proxy. Couldn't connect to server. Let's try restarting the Tor. Perhaps it's a bad connection. That happens sometimes. So Tor restart. Okay. And then we try it again. Okay. Connected to proxy. This time it didn't even give an error message. Let's see what this error code 91 is. If we go back to the RFC, so RFC SOX 4, and we go down here, request rejected or failed. I will try once again to restart the service. Perhaps we are unlucky with the connection. So let's do like this. And then we run Toralize again. At least it's able to intercept the connect function, as we can see by this connected to proxy. But it doesn't really succeed in connecting. Let's just see that this one is up and running. Yes, and it's listening on port 80, right? Let's do it just like this. Okay, I don't have telnet here. Let's run it from this instead. So env telnet is port 80. Okay, it's the server that's not responding. That's weird. Host. Let's try something else. Let's do, I think we should be able to do a regular host name. This is a Swedish site that shows the IP. If we do make this work though, that's not going through the Tor network, the actual DNS request. So the DNS request probably goes outside of the Tor network, and then the actual IP connection goes through. So couldn't connect to server. Weird. Does anything work? Google SC. Yeah, there's nothing wrong with the routing. But we need to try something else. What if we do a host on this site and we Toralize a curl HTTP and this IP instead? Are we able to connect directly to this one? Okay, that works. Let's look through the code. Perhaps we did miss something. So what happens right here? We set this to the regular connect function. We initialize a new socket and we connect to the proxy with a proxy port using this the regular connect function, and we manage to get connected to the proxy. Everything is fine this far. Perhaps there's some problem with when we grab the IP address. So rec equals request struct sock address in. Perhaps we should not send the reference. What if we were to do like this instead? cd code and Toralizer, and we need to run make, and then we do host ip.sc, and we do Toralizer curl http and this IP. Okay, so now it works, and we should be able to see the IP here, I think, somewhere. Okay, it seems that we go through some kind of middle server. It probably only works against Swedish IP addresses, and we probably don't come from a Swedish IP through the Tor network. We need to try something else. What if we were to do... First, we can test regular first. So if we do host... what is my IP.com, we do a regular curl, and we get an error code. Okay, we need to send the host name, and I don't think that'll work, but let's try it again. So curl, or it will work when you do it right here, but I don't think we will get a response. No. Let's just do Google then. So host google.com, and we do Toralizer curl http and this IP. Okay, that works. What if we do a host name? Does it even try to resolve that? Yeah, it works. But as I said, be careful by doing that, because only the IP connection will be private, not the DNS request. But as you can see, we are able to traverse the proxy, and we are able to Toralize any command using this tool. So that's the end of this series. I hope you want to subscribe and like if you think it deserves it. And there will be more interesting videos in the future. Thanks for watching, and thanks for today.